Something strange is moving through our solar system again. Astronomers have named it 3I/Atlas, the third confirmed visitor from another star. It came from the deep dark between solar systems, traveling for millions, perhaps billions of years before finally passing through our neighborhood. At first glance, it looks like a comet, but as new photos and data pour in, scientists are realizing that it may not behave like any comet we've ever seen before. And some of what they've discovered has reignited old fears. What if these interstellar visitors aren't just random chunks of ice and rock? What if they carry secrets or dangers from worlds far beyond our reach? The history of human observations of interstellar objects. For much of the 20th and early 21st century, astronomers speculated that objects might drift between stars, passing through the void of interstellar space and occasionally entering our solar system. These ideas rested on sound physics, gravitational interactions, star formation dynamics, and the ejection of small bodies from planetary systems, but remained untested by direct observation. Only in the last decade did our telescopes and surveys reach the sensitivity, coverage, and analytical capability to detect such fleeting visitors. When the first confirmed interstellar object arrived, it changed the paradigm. That first case was 1T Oumuamua, discovered on the 19th of October 2017 by the Pan-STARRS, one survey telescope in Hawaii. At first, it appeared like an odd asteroid on a bound solar orbit, but follow-up observations of its trajectory revealed something far more exotic. It had a hyperbolic orbit, traveling fast enough and on a path shaped in such a way that it could not have come from the solar system. The eccentricity of its path was well above the threshold for objects captured by the Sun's gravity, meaning that it arrived from beyond and would depart again. Scientists quickly labeled it the first confirmed interstellar object to pass through the solar system. Its name, Hawaiian for scout or messenger from afar arriving first, underscored the sense that this was something new, a visitor from another star system. Oumuamua appeared elongated, perhaps up to 400 meters wide and potentially 10 times as long as it was wide. It had no obvious cometary tail, no clear outgassing signature, and yet it showed slight non-gravitational acceleration as it left the inner solar system, which some argued came from a subtle thrust of gas or other process. Because it was detected only after passing its perihelion, aka the closest approach to the Sun, the length of time available to observe it was limited, roughly 80 days of arc. This meant that while it proved interstellar objects exist, it left many open questions. Was it a comet, an asteroid, a fragment of an exotic world, or something else? Scientists noted that although one object does not a class make, this one forced the recognition that our solar system is not a closed system. Just 2 years later, the next breakthrough arrived with 2I/Borisov, discovered on the 30th of August 2019 by amateur astronomer Gennady Borisov. This object also followed a clearly hyperbolic orbit, making it unbound to the Sun and thus interstellar in origin. Unlike Oumuamua, however, Borisov exhibited classical cometary behavior. A coma and tail developed as it approached the Sun, dust and gas were observed, and it gave astronomers a chance for more extended study. Detailed observations revealed that it contained unusually high concentrations of carbon monoxide compared to water ice, far more than typical solar system comets at similar distances from the Sun. Moreover, studies suggested it was extraordinarily pristine, having not undergone intense solar or stellar radiation that alters many other comets. In essence, Borisov gave us a more complete picture of what an interstellar comet can look like, how it behaves, and how it might differ from familiar bodies. Yet even then, the sample size remained one, intriguing and rich in data, but singular. The arrival of these two objects changed our observational framework. We began to expect that interstellar objects are out there, drifting across the galaxy, occasionally passing through our solar system. But we also understood how rare the opportunity is. Both detections required the right survey conditions, the right geometry, and the right timing. They also highlighted the necessity for rapid follow-up. As these objects accelerate away from the Sun's influence, the window for study is short. In July 2025, the story advanced once more when 3I/Atlas was discovered. The network known as the Asteroid Terrestrial Impact Last Alert System, or ATLAS, in Chile, spotted it on the 1st of July 2025, and follow-up work confirmed its interstellar origin. It was officially catalogued as the third interstellar object identified, marking a milestone, 3 such objects in under a decade. Because it was discovered comparatively early in its inbound path, scientists anticipate a longer observation window than prior objects allowed. This offers hope for deeper study, perhaps providing a richer comparison across interstellar visitors. The sequence of these observations, first Oumuamua, then Borisov, now 3I/Atlas, maps a journey from unexpected novelty to emerging pattern. Human observation of interstellar objects, therefore, can be seen as 3 acts: recognition, characterization, and pattern building. The first discovery forced acceptance that material from other systems can cross our path. The second allowed detailed compositional studies and behavior comparison. The third now opens the door to begin understanding diversity within this class. Moreover, the interval between discoveries reflects both the rarity of such visitors and the increasing power of our survey instruments. As we launch larger telescopes, automate sky scans, and develop more rapid follow-up systems, the chance of catching more such objects improves. An amateur astronomer spotted Borisov. Survey telescopes made possible all 3 discoveries, and teams around the world scrambled to mobilize resources once detection occurred. We have learned that recognizing an object is only the start. Capitalizing on that recognition requires coordination, instrumentation, and speed. Each object brings a narrow time window. Oumuamua had only weeks, Borisov somewhat longer, and 3I/Atlas even longer still. With each new object, our vantage broadens, from our solar system's familiar family to the wider ecosystem of the galaxy. Humanity, with its tools and curiosity, is reaching beyond the Sun and catching proxy fragments of other worlds. Each detection deepens our appreciation of how connected our system is to the rest of the galaxy. Why interstellar objects are rare and valuable. Typical comets and asteroids orbit the Sun. They formed in the protoplanetary disk that surrounded our young star, and their journeys are bound to our solar system's gravitational landscape. In contrast, an interstellar object arrives from afar, ejected from another star system, traveling through interstellar space, then passing through our region of the galaxy. Because they come from other systems, interstellar objects offer the possibility of carrying materials, chemistry, and structural history that are entirely foreign to our solar system, whereas the comets and asteroids we study have a shared heritage with the Sun, with planetary formation processes in our local region. An interstellar visitor could reflect a very different set of conditions, a different star, a different disk, a different ejection history. That difference is what grants them their value. The composition of the object Borisov, for example, showed an unusually high ratio of carbon monoxide to water compared to typical solar system comets, thereby offering a window into how another planetary system may have formed and evolved. Thus, in one fleeting pass, an interstellar object can bring us data from a different star system, something we cannot easily access otherwise. The reason we see so few of these objects lies in the combination of their origins, their number, the vastness of space, and observational limitations. Even though theoretical work suggests that there are enormous numbers of such objects wandering the galaxy. Some estimates propose that there could be on the order of 10 to the power of 25 or 26 such bodies in the Milky Way's disk. Detecting one is extremely challenging. The first challenge, size and brightness. Many interstellar objects are small, perhaps only hundreds of meters across, and they reflect very little sunlight. In the emptiness of space, they are faint. This makes them hard to spot against the vast background. The second challenge is speed and time window. They tend to move very quickly relative to the Sun and the Earth. By the time they are detected, they may already be moving away. limiting the time scientists have to study them. For instance, Oumuamua was already on its way out when it was discovered, which limited the amount of data we could collect. The third challenge is observational coverage. The sky is large, and our survey telescopes must scan wide areas, often repeatedly, to catch unexpected visitors. Only when survey systems are capable enough, and happen to catch the visitor in the narrow window when it's bright and in reach, can we identify them as interstellar. Even if such objects enter our solar system's neighborhood more often than we realize, many will remain undetected. Studies suggest that while interstellar objects may be abundant in the outer reaches of the solar system or the interstellar medium, most evade detection because they are faint, distant, or simply pass by when we are not watching. For example, a study suggested that interstellar objects may outnumber solar system objects in the distant Oort cloud region, but we have little observational access there. This means that the ones we do detect are the ones we caught under favorable conditions. Because of their rarity, each interstellar object becomes highly valuable. From a scientific perspective, they are direct material samples of other star systems. While much of what we learn about other planetary systems comes through indirect methods, telescopic measurements of exoplanet atmospheres, disk observations, or spectral signatures, an interstellar object offers physical matter created in another system, now within our study range. That gives us a chance to test theories of planetary system formation, material ejection, chemical abundances, and interstellar travel of small bodies. For instance, as NASA notes, the discovery of Oumuamua reinforced the idea that planetary systems eject material into interstellar space after formation. That kind of insight amplifies the value of each detection. Moreover, because each interstellar object presents a snapshot of another system at another time, we can compare whether the building blocks of planets and comets are broadly similar or radically different across the galaxy. Each interstellar visitor prompts us to ask bigger questions. What kinds of materials are floating between the stars? What histories do they carry? Could some of those materials have influenced our own system? These objects are messengers, in a sense, not just of rock and ice, but of another system's story. While they are rare in terms of detection, they may not be intrinsically extremely rare in the galaxy. Some researchers argue that they may even be common as wandering bodies. The fact that each one may be unique, formed under different conditions, ejected by different mechanisms, and arriving with different compositions, means that each new detection has the potential to extend and challenge our understanding of planetary formation, galactic material exchange, and our own place in the universe. The role of survey telescopes in detecting interstellar visitors. The discovery of the Interstellar Visitor 3I/Atlas owes much to the dedicated and increasingly sophisticated network of survey telescopes sweeping the skies each night. These observatories, built originally for finding near-Earth asteroids and transient events, have now become critical players in detecting rare interstellar objects. One of the key instruments in this effort is ATLAS, a system of small but nimble telescopes that automatically scan large swathes of the sky in search of moving or changing objects. ATLAS comprises 4 0.5-meter telescopes, 2 in Hawaii, 1 in South Africa, and 1 in Chile, designed for wide-field, rapid-cadence imaging of the night sky and alerting astronomers when something new appears. The role of these survey systems is vital because when an interstellar object arrives, it doesn't announce itself. It appears faint and fast, often in a region of sky with many moving objects already, and then quickly accelerates through the inner solar system. Without a wide-field survey constantly imaging the sky and automated software to pick out moving points of light, many of these visitors would simply pass unnoticed. In the case of 3I/Atlas, the Atlas telescope at the El Source Observatory in Chile reported the object on July 1, 2025, about 670 million kilometers from the Sun. Because Atlas scans wide and repeatedly, it was able to detect something unusual, an object with motion inconsistent with a normal bound orbit. That triggered further follow-up by larger telescopes. Importantly, The detection of 3I/Atlas also benefited from pre-covery and cross-survey data. The Zwicky Transient Facility, or ZTF, a robotic survey camera at Palomar Observatory designed to detect fast-moving or transient phenomena, had images of the object on June 28, 29, which helped refine its orbit and establish its interstellar character. This highlights how the network of survey telescopes, each designed to scan large areas of sky, detect objects in motion, and share data rapidly, is critical in discovering and characterizing interstellar visitors. Beyond Atlas and ZTF, many telescopes participated in rapid follow-up once the object was flagged. For example, the Las Cumbres Observatory network, with telescopes in multiple continents, provided observations just days after discovery to refine the object's brightness, motion, and appearance. The speed of response is key. Once a moving object from interstellar space is detected, larger telescopes are mobilized to capture images and spectra that reveal composition, activity, and trajectory. The technological improvements and greater coverage of surveys have dramatically improved our ability to catch these rare travelers. Now, with survey telescopes that scan faster, more widely, and with better software to identify moving objects, the likelihood of seeing an interstellar object improves. For instance, the surveys now image larger portions of sky more frequently, and machine learning or automated pipelines flag objects that move faster than typical solar system comets or asteroids. They also cross-match observations to look back at earlier images to build a trajectory. In the case of 3I/Atlas, pre-covery data from the Transiting Exoplanet Survey satellite and other archives supported the discovery. Another element is that survey telescopes often operate robotically, meaning they can respond rapidly and continuously without requiring new manual scheduling each night. They produce massive amounts of data, and the automated tracking of moving objects can highlight candidates for follow-up within hours. Once Atlas reported the detection, alerts went out and many observatories turned to observe. That collaborative network is a hallmark of modern astronomy. The speed matters because the object moves fast. It is traveling at about 61 kilometers per s relative to the Sun. Many telescopes are designed for deep but narrow imaging of specific targets like galaxies or exoplanets. But to catch an interstellar object, you need to hunt the whole sky. Survey systems cover large swaths hourly or nightly, searching for points of light that weren't there before or that move across the background of stars. Atlas, for example, is optimized for detecting near-Earth objects, but its wide-field nature makes it well-suited to catching objects on odd trajectories, including interstellar ones. When the survey telescope flags something, the next step is orbit calculation. Where the object is, how fast it's moving, and whether its motion is consistent with a bound orbit or a hyperbolic one must be determined. Once that is known, scientists mobilize spectroscopic and photometric observations to probe its composition and behavior. Survey telescopes can provide the initial detection, but larger instruments then provide the deep science. Survey telescopes are becoming more capable and numerous, meaning we may expect more interstellar objects to be found. The Vera C. Rubin Observatory, with its legacy survey of space and time, will scan the sky deeply and repeatedly, vastly increasing the chance of catching objects like 3I/Atlas. Scientists note that our detection rate could increase substantially as coverage improves. Survey telescopes operate as the first link in the chain of discovery for interstellar visitors. They continuously monitor wide fields, flag moving or changing objects, issue alerts, and provide initial data for orbit determination. Without that groundwork, an object passing through might escape notice altogether, or be spotted too late for detailed study. The data from surveys are also essential for traceback analysis: how long the object has been seen, whether archival images exist, and how quickly follow-up can proceed. In that sense, these telescopes are not just tools for finding near-Earth hazards, but portals to the outer reaches of galactic material. Naming conventions. What 3I/Atlas means. When an object such as 3I/Atlas is announced, the naming codes layers of meaning: where it came from, how it was discovered, and how it is classified. In this case, the name 3I/Atlas conveys immediately that this is not a typical solar system comet or asteroid, and also points to the survey that first observed it. The I stands for interstellar. The number 3 indicates that this is the third confirmed interstellar object to be recognized passing through the solar system. The combination 3I therefore immediately flags this object as special, another interstellar visitor, a rarity. Following that, the /Atlas suffix links the object to the survey program which made the first public reported observation. Thus, 3I/Atlas reads as the third interstellar object discovered by Atlas. In parallel to that designation, the object also carries the more typical cometary nomenclature used by the International Astronomical Union and the Minor Planet Center. Its provisional designation is C2025N1 Atlas. In that designation, the C/ prefix means non-periodic comet, that is, an object not known to return on a regular orbit. 2025 is the year of discovery. N1 indicates the half-month of discovery, and that it was the first such object catalogued in that period, and Atlas again credits the discoverer. Together, the two names describe different facets. One emphasizes its interstellar nature, 3I/Atlas. The other treats it as a comet within the catalogue system. The way naming works for interstellar objects has been standardized in recent years. The I suffix is distinct from typical comet-asteroid designations, which might use C/ or P/ for periodic comets, or A/ and D/ for asteroids and defunct comets. Using this system helps astronomers immediately recognize how an object should be treated. Traditionally, comets were named after individuals, such as Comet Hale-Bopp, but in modern large survey times, many comets are given the survey name. Since Atlas is the program that found the object, its name appears in parentheses in the provisional designation and as the suffix in the interstellar name. This both honors the discovery and provides a metadata tag for future reference. The adoption of dual names may sometimes cause confusion for non-specialists, but within the astronomy community, it is meaningful. The two names emphasize different aspects of the object, its interstellar origin and its comet-like behavior and discovery details. Establishing the interstellar origin of 3I/Atlas. For any object orbiting the Sun, a key parameter is its eccentricity, denoted E. If E is less than 1, the orbit is elliptical, and the object is bound to the Sun. If E is equal to 1, the orbit is parabolic. If E is greater than 1, the orbit is hyperbolic, and the object is not gravitationally bound to the Sun. It will pass through and keep going. In the case of 3I/Atlas, the measured eccentricity is around 6.1 to 6.2, a value far beyond the bound regime. This alone is a smoking gun. An object on such an open-ended trajectory cannot be a long-term member of our solar system. Secondly, when an object enters the solar system from far away, one can measure its inbound excess velocity, or the speed it has relative to the Sun at a large distance, called v. For 3I/Atlas, follow-up astrometry shows an inbound velocity of approximately 5860 km/s relative to the Sun. This speed is far higher than typical solar system comets or asteroids, many of which have heliocentric speeds in the tens of kms range when coming from distant Oort cloud regions. Indeed, comparison with previous interstellar visitors reinforces the anomaly. For instance, Oumuamua had a much smaller hyperbolic excess velocity, and Borisov also lower. The large speed of 3I/Atlas therefore supports the case that it came in from the depths of interstellar space, not just scattered within the solar system. Third, the approach direction and orbital inclination provide further clues. The orbit of 3I/Atlas is highly inclined and essentially retrograde relative to the ecliptic plane. The angle is roughly 175 degrees relative to the Earth's orbital plane. A retrograde and inclined trajectory is a strong sign of an origin outside the normal plane of solar system objects, which tend to cluster near the ecliptic in roughly prograde orbits. Furthermore, tracing the path back in space shows the object arriving from the general direction of the constellation Sagittarius, toward the inner region of the Milky Way. This was not a case of the object being captured or perturbed from a bound solar orbit in a way we've seen many native comets. Rather, its direction and speed simply pointed to a foreign origin. Fourth, the context of gravitational dynamics. An object that appears hyperbolic but actually is bound might owe its excess velocity and open orbit to a strong slingshot from a massive body in the solar system like Jupiter, or from the Sun itself. For 3I/Atlas, the evidence strongly indicates that no plausible planetary encounter within the solar system could have imparted the needed velocity or changed its path sufficiently to generate an eccentricity of over 6. The combination of speed, orbital shape, and retrograde path lines up far better with inbound interstellar origin than solar system origin. Taken together, the argument is compelling. Moreover, the object is active, meaning it displays a coma, so it is behaving much like a comet, but on a path that cannot have been forged here. Researchers modeling interstellar object populations find that 3I/Atlas fits the predicted velocity and radiant distribution of a thin disk population of ejected planetesimals. Furthermore, pre-recovery observations and follow-up astrometry extended the observation arc back sufficiently to confirm the orbit with a high degree of confidence. Orbital simulations indicate that after passing perihelion around late October 2025 at about 1.4 AU, the object will exit the solar system entirely, heading back into interstellar space. The fact that it will not be captured, will not enter a bound orbit, and instead will continue outward, reinforces that this is a one-time visitor. In contrast, many solar system comets are bound and will return after one or more orbits. That difference is foundational. One subtle point is that some long-period comets that originate in the Oort cloud can display eccentricities slightly above 1 due to perturbations by planets or passing stars, but they tend to cluster near 1. In this case, however, the very high eccentricity of 6 places 3I/Atlas in a distinct category. Scientific teams also trace the object's motion backwards through the galaxy to look for plausible origin star systems or stellar associations. As one recent study shows, integration of its orbit within the galactic potential and cross-matching with stellar motion databases show that while exact progenitor star remains unconfirmed, the likely origin zone is the thin disk of the Milky Way, and given the high relative velocity, it appears to have drifted through interstellar space for billions of years. Thus, the establishment of the interstellar origin of 3I/Atlas is based on a convergence of physical trajectory evidence, velocity analysis, comparison with bound populations, and modeling of progenitor dynamics, trajectory and orbit, where 3I/Atlas came from and where it's going. The trajectory of 3I/Atlas, how it entered our solar system, where it will go, and the path it traces, is a critical part of understanding this rare visitor. In the weeks following its discovery, astronomers collected astrometric measurements, pre-recovery images, and applied orbital mechanics to draw a nearly complete picture of its journey. The details reveal not only its interstellar origin, but also its interaction with our solar system on its brief passage. The first key parameter is the perihelion distance, how close the object will come to the Sun. For 3I/Atlas, that distance is approximately 1.356 AU from the Sun, which is about 1.356 times the mean distance between the Earth and the Sun, or roughly 203 million kilometers. That means its closest point is just inside the orbit of Mars, since Mars's orbit varies around 1.5 AU, but still well outside Earth's orbit. The predicted time of perihelion passage is around the 29th of October 2025. With that perihelion nearly fixed, scientists also track the object's minimum distance from Earth. While it does not come particularly close to Earth, the figure stands at about 1.8 AU, approximately 270 million kilometers, at its closest approach to our planet. That relatively distant approach means there is no risk of impact, but it also underscores the challenge of observing such a faint object. more distant than Earth's orbit, and thus fainter and less well placed for some telescopes at times. 3 I/Atlas moves on a retrograde path, meaning it travels opposite the direction of the planets around the Sun. Such a path is unusual for solar system objects, which mostly orbit prograde and at lower inclinations. The path is determined through a combination of observation and modeling. Astrometric data flow in from discovery, pre-recovery images, and follow-up observations. In the case of 3 I/Atlas, pre-recovery images from facilities such as the TESS satellite and archival survey telescopes extended the observation arc, improving the precision of the orbit. These measurements feed into orbit-solving software that computes the best-fit path around the Sun, accounting for gravitational perturbations from the Sun and other bodies, though minor in this case, and then extrapolate past the Sun to a hyperbolic trajectory. Because the eccentricity is so large, the aphelion, or farthest point, effectively lies beyond the solar system, and the object will not complete an orbit. After perihelion, 3 I/Atlas will swing outward and exit the inner solar system. It will pass Mars's orbit close to 0.19 AU away on the 3rd of October 2025, according to some calculations. Some projections list additional planet-close passes. For example, passing Venus at about 0.65 AU on the 3rd of November 2025, Earth at 1.80 AU on the 19th of December 2025, and Jupiter at 0.359 AU on the 16th of March 2026. As it recedes, its brightness will fade, and solar elongation will make observation harder, especially as it heads into conjunction with the Sun. The nearly 1.356 AU perihelion means the object approaches somewhat close to the Sun compared to many comets, but not extremely close compared to sun grazers. Because it is showing a coma, and because it approaches within the orbit of Mars, the solar heating will drive activity. But given its high speed, that activity will be compressed into a shorter time span than slower comets. Its rapid inbound and outbound motion reduces the time it spends in high insolation regimes, meaning any dust and gas driven off the surface will be visible for a relatively short interval. Because of the speed and trajectory, the object's path through the solar system is steep and fast. The observation window is therefore limited. Observers must rely on precise predicted positions to point telescopes and schedule observations before it moves into solar glare or falls behind the Sun from Earth's viewpoint. The orbital path also allows scientists to trace the incoming direction and outgoing path. The inbound approach appears to be from the general direction of the constellation Sagittarius, from the southern celestial hemisphere, which is somewhat surprising given earlier expectations that interstellar visitors might arrive more often from the solar apex direction. The outgoing direction will carry it back into interstellar space, eventually leaving the gravitational reach of the Sun altogether and traversing the galaxy as a free interstellar traveler once more. Because the orbit is hyperbolic, there is no return. Once it passes perihelion and continues outward, it will cross the heliopause and enter the galactic environment. Its path may be charted for some time, but its journey lost amidst many interstellar objects. The orbit determination also includes uncertainties. While the basic parameters are clear, refinements continue as more observations come in. Because initial arcs were relatively short, uncertainties in time of perihelion, close approach distances and future path remain. However, with pre-recovery data extending back to May or June 2025, the observation arc is substantially improved. Speed and kinematics, how fast it's traveling. According to the latest data from NASA, when 3 I/Atlas was discovered at about 670 million kilometers from the Sun, it was moving at roughly 61 kilometers per s, which is about 137,000 miles per hour or 221,000 kilometers per hour relative to the Sun. As the object approaches perihelion, its speed will increase further due to the Sun's gravitational acceleration. Models suggest that at its closest approach to the Sun, 3 I/Atlas may reach speeds of about 68 kilometers per s relative to the Sun. Thus, its kinetic profile is extreme by any small body standard. High speed has direct implications for observational strategy and mission planning. Because the object moves so quickly through the inner solar system, the window to study it is relatively narrow. It passes by, brightens, reaches perihelion, and then begins to recede at high speed. Telescopes must therefore be ready to image it, perform spectroscopy, and measure its physical and chemical properties before the viewing geometry becomes unfavorable. The faster an object moves, the more quickly it sweeps past optimal observing positions, and the more challenging it is to schedule follow-up. For possible spacecraft missions, which remain highly challenging at these speeds, the delta-V requirements become enormous. One analysis states that intercepting 3 I/Atlas after its discovery would require propulsion beyond current capabilities, due largely to its high outbound speed and hyperbolic trajectory. Kinematic data, like speed, can give insight into the object's past. A high V suggests that 3 I/Atlas has traveled through interstellar space for a long time, possibly accumulating velocity changes through gravitational interactions in the galaxy. For instance, one modeling paper estimates that with V approximately 58 kms, the object is likely several billion years old, perhaps between 3 to 11, based on comparisons to stellar velocity dispersions. Thus, speed isn't just a number. It contains within it traces of the object's galactic history. Oumuamua had an excess velocity of 26 km per s and an eccentricity of 1.2, while Borisov approached at 32 km per s with an eccentricity 3.4, 3 I/Atlas s. Kinematic extremity reinforces the idea that interstellar objects may span a wide range of speeds and histories, and that each one offers a distinct window into its origins. From a science operations standpoint, the high speed presents both opportunities and constraints. On the opportunity side, the high kinetic energy means the object is more likely to retain traces of primordial materials from its parent system, whether in dust grains, volatiles, or isotopic signatures. Its rapid passage means its subsurface ices may haven't been extensively processed in our solar system environment, and its dynamical journey may preserve more of its original state. That makes measuring its outgassing, dust production, and composition all the more valuable. On the constraint side, however, because it is moving so fast outward again, there is a shrinking interval for high signal data collection before the object becomes too distant or too faint. If key observations are missed now, they cannot be redone. In a hypothetical future, where one might attempt to match or intercept such an object, the speed sets the bar for required mission design. A spacecraft would have to launch quickly, achieve high delta-V, possibly perform an Oberth maneuver near the Sun, and chase a target whose approach vector, speed, and outbound path are all extreme. In the case of 3 I/Atlas, analyses suggest that such a mission window has already passed or would demand technology beyond our current reach. That reality highlights the urgency and rarity of studying such objects in situ. As the object recedes post-perihelion, its speed will gradually drop as it leaves the Sun's immediate gravity. But because its V is large, it will continue to escape the solar system at high residual speeds. In effect, it is not bound and will never return. That outgoing motion means it becomes an arrow leaving our solar system. Physical characteristics: what 3 I/Atlas looks like. Understanding the physical appearance of 3 I/Atlas gives us a direct visual connection to this visitor from another star system. Despite the vast distances and faint signals, astronomers have managed to capture its nucleus, a surrounding cloud of dust and gas and faint indications of a tail. Each component tells part of its story: what it looks like, how it behaves, and how it compares to familiar comets within our solar system. Beginning with the nucleus, this is the solid, icy rocky core of the comet, its heart, though in practice hard to resolve. Observations by the Hubble Space Telescope on the 21st of July 2025 provided high-resolution views when the object was still at some distance from the Sun. These images enabled an estimate of the nucleus size, The upper limit for the diameter is about 5.6 kilometers, though a lower bound is around 0.32 kilometers, yielding a very wide size range. The large uncertainty comes because the nucleus is enveloped in a bright coma, making it difficult to separate nucleus light from the surrounding dust and gas. The images show a teardrop-shaped bright region and a dust plume emanating sunward, suggesting significant active sublimation of ices on the sun-facing side. Importantly, although initial ground-based estimates had entertained even larger sizes, about 10 to 20 kilometers, the Hubble data refined this significantly. In particular, a paper based on Hubble data set a radius upper limit of less than 2.8 kilometers, assuming a low reflectivity or albedo of the surface, and a lower bound of about 0.16 kilometers radius if the activity were driven by very volatile ices like carbon monoxide. Thus, while the exact size remains uncertain, the likely nucleus is perhaps on the order of 1 kilometer or less, comparable to or somewhat larger than the core of Borisov. Surrounding that nucleus is the coma, the cloud of gas and dust released when the sun's heat drives sublimation of ices on the surface. The coma of 3I/Atlas is clearly visible in images. The object appears fuzzy rather than point-like, its light spread out due to the dust environment. On July 21st, when Hubble observed it, the comet was still at 3.8 AU from the Sun, yet already showed active dust ejection. The dust loss rate, derived from brightness profiles, is estimated at between 6 and 60 kilograms per second, depending on dust particle size, at that distance. Such activity at that distance suggests relatively volatile ices or efficient sublimation. An unusual morphological detail in the coma of 3I/Atlas is the presence of a sun-facing plume or anti-tail-like feature, an elongation of the coma toward the sun rather than the classic tail pointing away. Analysis of images taken at 3.8 AU showed that the coma was elongated in the direction of the sun, and modeling indicates this is likely due to anisotropic sublimation of ice grains on the sunlit side, producing large particles that survive longer and form the extension. Later, the comet developed a more standard anti-solar tail, or a tail pointing away from the sun, as dust particles were pushed out by solar radiation pressure and solar wind, becoming more apparent as the viewing geometry evolved. Early images from Hubble in July show a faint and broad tail pointing roughly away from the sun, but only visible as a faint extension, perhaps only tens of arcseconds long at that stage. By late August, ground-based telescopes like Gemini South observed a tail length of 30 arcseconds, which is on the order of tens of thousands of kilometers, and further elongation as the comet approached perihelion distances. The tail is composed of small dust particles released from the nucleus and pushed by sunlight and solar wind into trails. Because 3I/Atlas is traveling at high speed and still at some distance, its tail does not yet show the dramatic structure of many slower solar system comets when they approach very near the sun. That means observers must be alert and using large telescopes to pick out the tail features. Brightness-wise, the comet is relatively faint compared to many comets that become visible to the naked eye. As of mid-2025, it was at apparent magnitudes of 16 to 17 when discovered at 4.5 AU and is expected to reach perhaps magnitude 11.5 at peak, given its distance and activity. The coma and tail contribute to the brightness, yet the large distance and its small nucleus size mean that it remains modest in brightness. Another notable attribute is the color evolution of its coma. Photometry from the Atlas network indicates that 3I/Atlas shifted in color, from redder to near solar color, coinciding with the appearance of a more prominent tail. This suggests a change in dust grain production. Initially reddened surface dust grains, later more transparent icy grains being produced as the comet warmed and increased activity. In comparing 3I/Atlas with solar system comets, several differences and similarities stand out. Similar to many solar system comets, it shows an active coma, dust loss, a tail, and morphological changes as it approaches the sun. But in contrast, it differs in its earlier activation at larger heliocentric distances and the unusual sunward elongation of the coma early on. The inference of a relatively small nucleus, perhaps less than 1 kilometer, also places it among the smaller documented active comets, though uncertain. While solar system comets of similar size are well known, the fact this one came from another star system makes every structural detail more significant. The dusty plume seen in the Hubble images, pointing sunward, is particularly unusual compared to typical comets and may reflect the unique heritage and environment of this interstellar visitor. The anti-tail phenomenon is also rare among comets and may indicate different dust grain properties or sublimation history. The modeling paper suggests that the snowline for large particles on the sun-facing side was farther out because of slower sublimation of large grains, thereby producing an elongation toward the sun. At present, no statistically significant rotation period has been discerned from the pre-Covey light curve obtained by TESS between May and June 2025, though the coma dominated the brightness, complicating rotation detection. Given its rapid transit through our solar system, changes in morphology may be captured only briefly, adding urgency to observational campaigns. Observing the structure also helps in planning any future missions. Knowing the coma size, dust loss rate and tail extent helps determine how bright it might become, how quickly it will fade, and what telescopes can best capture it. For example, the early dust loss rate suggests active outgassing sufficient to produce a visible coma at large distance, making early observations possible even when the object was relatively far from the Sun. As the nucleus gets closer and warmer, the coma will expand and the tail may lengthen. But concurrently, the object moves quickly and solar elongation becomes less favorable, so observational windows shrink. What the observations reveal about its makeup. The chemical composition of 3I/Atlas gives us a rare and powerful window into material from another star system. Spectroscopic observations of its coma and surrounding dust have revealed unexpected and distinctive signatures: gases, ices, dust, and trace atoms that together suggest an origin quite unlike typical solar system comets. One of the most striking findings is the dominance of carbon dioxide, or CO2, in the gas coma. Using the James Webb Space Telescope, or JWST, on the 6th of August 2025, astronomers found that 3I/Atlas's coma has a CO2 to H2O mixing ratio of approximately 8, among the highest ever measured in a comet. In other words, if the amount of water gas expelled from the nucleus is taken as 1, the amount of carbon dioxide gas is roughly 8 times greater, an inversion of what is typical for solar system comets. In standard comets, water vapor tends to dominate. The extraordinary ratio suggests that either the nucleus is intrinsically rich in CO2 ice relative to water ice, or that sublimation of water has been suppressed relative to CO2 for some reason. Complementing the JWST data, the SPHERE-X mission detected a large CO2 coma extending at least 348,000 kilometers in radius around 3I/Atlas during observations in August 2025, when the object was about 3.15 AU from the Sun. That extended CO2 distribution emphasizes how plentiful this volatile is in 3I/Atlas's makeup and how early activity begins compared with typical comets. Water vapor and other gases are present, but relatively faint in comparison. The faint water presence is itself noteworthy. While water ice is almost always abundant in comets from our solar system, in 3I/Atlas, the water outgassing appears to be suppressed or delayed. Some models suggest that heat cannot penetrate the nucleus easily, or that large dust grains insulate underlying water ice, whereas CO2, being more volatile, sublimates earlier and more strongly. Because CO2 can sublimate at colder temperatures at greater distances from the Sun than water does, this provides a mechanism for the early activity seen in 3I/Atlas when it was still relatively far from the Sun, well beyond Jupiter's orbit in some cases. Other gases detected in the coma include carbon monoxide, or CO, and carbonyl sulfide, or OCS. The JWST observed spectrum recorded emissions at wavelengths corresponding to CO, OCS, and H2O, though CO2 was dominant. The presence of these additional volatiles supports a more complex volatile inventory than just CO2 and H2O and gives clues to the formation environment of the object, indicating volatile ices that formed beyond a certain ice line in a protoplanetary disk. Dust and fine-grained material around 3I/Atlas also reveal chemical and isotopic clues. Analyses indicate that the dust is composed of relatively large grains, and that the dust color is reddish, which may indicate the presence of irradiated organic compounds, such as tholinsm, which are complex organics formed by irradiation of simple ices. In addition, isotopic ratios of carbon appear broadly similar to those found on Earth, suggesting that the material and the star system that produced it might share some chemical pathways with ours. The JWST dataset notes that while the CO2 dominance is unusual, the isotopic makeup of carbon shows little deviation from solar system norms. There are also tantalizing but more controversial findings. Some ground-based observatories have reported detection of atomic nickel vapor in 3I/Atlas's coma without an accompanying ion signature, something nearly never seen in natural solar system comets. While this finding remains under review and debate, it nevertheless opens up intriguing questions about the cleavage of certain metals or unusual processing in the parent system of 3I/Atlas. The possibility that uncommon elemental abundances appear is integral to the case that 3I/Atlas formed under different conditions from typical solar system comets. From these chemical data, scientists are learning what the makeup of material from another star system can look like and how it may differ. The CO2-rich composition suggests that 3I/Atlas may have formed in or beyond the CO2 ice line of its parent stellar system's protoplanetary disk, that is, the distance at which carbon dioxide condensed into ice, as opposed to remaining gaseous in the warm inner region. Such a formation location might result in higher CO2 ice abundance relative to water ice. Another possibility is that the parent system experienced high ultraviolet radiation or other strong processing, which removed or altered water ice more rapidly than CO2 ice, leaving a volatile signature skewed toward CO2. Furthermore, the early onset of activity, seen at larger heliocentric distances than typical, indicates that these volatiles are highly accessible and that the nucleus may have been preserved for a long time in a cold interstellar environment, experiencing little heating and thus retaining pristine volatile inventories. Because it is interstellar, 3I/Atlas may have drifted through space for billions of years. So contrary to many solar system comets, which have undergone repeated solar heating, its ices may be original remnants of the parent system's early era. That makes its chemical composition especially valuable as a window into ancient, extrasolar history. 2I/Borisov was rich in CO relative to water, but did not show the extreme CO2 dominance of 3I/Atlas. Meanwhile, Oumuamua lacked a clear coma and thus offered much less chemical data. The diversity among these three thus hints at a broad range of interstellar comet composition, and by extension, a broad variety of formation environments across the galaxy. The chemical composition of 3I/Atlas also has implications for how we view comet formation and planetary system evolution. If other star systems routinely produce CO2-rich icy bodies, that suggests that the inventory of volatiles delivered by interstellar objects to planetary systems, including possibly ours, may differ fundamentally from our standard models. Models often calibrated to solar system comets with water as the dominant volatile. This raises the possibility that the building blocks of planets and minor bodies around other stars may have different ice-volatile balances, and that our solar system's composition may not be universally representative. Because Atlas is shedding CO2 vigorously, the dust and gas environment will evolve rapidly, and the window for observing specific volatiles may close as it moves away from the Sun. As the CO2 sublimation dominates, water outgassing may increase closer to perihelion, if residual water ice remains in greater depths of the nucleus. Tracking how the chemical inventory evolves as the object moves inward gives insight into layering of the nucleus and processing history. Is 3I/Atlas an alien probe? While many astronomers classify Atlas as a natural comet, Harvard astrophysicist Avi Loeb and his colleagues have proposed a more provocative hypothesis: that 3I/Atlas might be an artificial object, potentially an alien probe. This theory has garnered attention due to several unusual characteristics observed in the object. Many of the arguments center on its trajectory. The object approaches the Sun on a hyperbolic path. What draws further attention is that its incoming path lies very close to the plane in which Earth and the other major planets orbit, the ecliptic. Loeb argues that the chance for a random interstellar object to enter at such a low inclination angle is extremely small. For instance, Loeb and colleagues estimate the probability of those alignments, approaching close to Venus, Mars and Jupiter in turn, at about 0.005%. They argue that such coincidences might suggest a directed mission rather than a random wanderer. In addition to trajectory, chemical and physical properties are flagged. The CO2-H2O mixing ratio raises the possibility that the object formed under different conditions or is made of materials not common in our solar system's comet population. Even more startling to proponents of the probe idea is the claim of nickel emission without corresponding iron. A news report quoting Loeb claims that 3I/Atlas is shedding nickel at a rate of about 4 grams per second, but without detectable iron, an unexpected metal ratio for a natural body according to comet analogues. In terrestrial industrial contexts, nickel tetracarbonyl is a refined compound, produced for specific engineering uses, which raises eyebrow-raising questions when applied outside Earth. The suggestion is that such a chemical signature might be more consistent with manufactured materials than with a simple ice rock body forming randomly in space. Observers also note the tail or absence of a conventional tail. Typical comets that enter the inner solar system develop visible tails. In the case of 3I/Atlas, some images reportedly show a glow in front of the nucleus rather than trailing behind, a phenomenon that Loeb describes as puzzling and not like any comet we've seen. The claim is that if the object is shedding material, it is doing so in a way that seems directed rather than simply being pushed by solar radiation and wind. That directional behavior can be interpreted as evidence of maneuvering or purpose rather than passive movement. Some of the early brightness estimates imply a nucleus size perhaps tens of kilometers across. In Loeb's view, the brightness and size may exceed natural expectations given the inferred frequency of such objects. He suggests that the detection of an object this large at this time may be unlikely if natural, prompting consideration of alternative explanations. The statistical argument is that we have seen only 2 interstellar objects before this, and yet this one presents unusual features, which could indicate we are not simply observing random natural bodies, but perhaps something engineered. Those who favor the alien probe hypothesis also highlight possible mission architecture features in its behavior. For example, Loeb argues that the object's perihelion occurs when it is hidden on the far side of the Sun from Earth. He calls that timing suspicious, raising the possibility that the path may have been intentionally planned to avoid detailed Earth-based observations at a critical point. The idea is that an artificial object might plan to avoid detection while performing a maneuver near the Sun, or using the Sun's gravity in a reverse Oberth maneuver to change trajectory. The argument is speculative, but serves to illustrate how supporters frame the data, from unusual passage geometry to composition anomalies to timing of the object's visibility to Earth. Supporters of the hypothesis emphasize that none of the elements alone proves artificial origin, but they argue that when taken together, the probability of all these being coincidental is low. One way this is framed: if the chance of one unusual feature is small, and then you multiply across several independent unlikely features, The resulting probability is extremely small under a simple natural object model. For example, Loeb quotes probability values such as 0.005% for the coincidence of orbiting plane alignment and planetary passes, though critics argue that such numbers are easily misinterpreted. The suggestion is that rather than seeing a natural body drawn at random from the population of interstellar objects, we might have caught a purposeful mission, or one part of a swarm of probes. If a visitor from another star system arrived, what would betray its artificial origin? Some say that an object with an unusual orbit, specific coordination to planets, anomalous composition and behavior inconsistent with natural physics as we understand it, would merit serious consideration. In other words, we might have to ask, could this be technology masquerading as a comet? The proponents of the probe hypothesis suggest that 3I/Atlas could meet several of those criteria. Yet it is important to note that the hypothesis remains a minority view in the community. Observational teams continue to collect data with telescopes and planetary rovers, aiming to refine size, composition, and trajectory further. Still, the cluster of remarkable features continues to fuel discussion, and for some researchers, it is a strong reason to keep an open mind about possibilities beyond our current assumptions. Evidence against the alien probe hypothesis. Many scientists advise caution, emphasizing that while the object presents some odd features, there are strong arguments against assigning it an artificial origin. One central line of reasoning is that 3I/Atlas behaves broadly like a natural comet, and that many of its anomalies may be accounted for by known or plausible natural processes. From the moment of its discovery, observers noted that 3I/Atlas exhibited a coma as typical comets do. According to data compiled by NASA, the object shows evidence of activity consistent with sublimation of ices. The ultraviolet detection of OH radicals implies water release, and the object was active at heliocentric distances of over 3 AU, which is unusual but not unprecedented. The presence of such signatures supports a natural object classification. The fact that 3I/Atlas is moving on a hyperbolic path is also consistent with the other known interstellar visitors, and therefore not alone suggestive of alien design. Critics of the alien probe hypothesis also point out that the data are still relatively sparse, and that drawing far-reaching conclusions from partial observations risks misinterpretation. For example, the claim that 3I/Atlas emits nickel without iron may hinge on limits of detection rather than true absence of iron. As one preprint notes, iron could be present below instrument thresholds. As such, what appears to be extraordinary chemistry may simply reflect limitations in measurement or an exotic natural chemistry from a distant star system with different elemental abundances. A recent article in Sky at Night magazine presents the case that 3I/Atlas shows no detectable non-gravitational accelerations that would be expected if artificial propulsion were present. The motion is well explained by solar gravity and normal cometary physics. The familiar pattern of dust and gas emission, coma development, and changing brightness all point to a natural body rather than a spacecraft. Regarding the unusual chemical ratios, natural models have been advanced to explain them. Rather than invoking alien engineering, scientists propose that 3I/Atlas may have formed in a part of its parent system near the CO2 ice line, or in an environment that exposed its ices to high radiation, altering volatile inventories. This scenario remains within the bounds of natural cometary science, just in a more extreme environment. The orbital alignment of 3I/Atlas also comes under scrutiny. However, the consensus among many astronomers is that while the alignment may be statistically uncommon, unlikely does not automatically equal engineered. The Guardian quotes multiple astronomers, noting that one can always find low probability events in the many possible detection windows, and that the alignment is not outside the realm of natural phenomena. In short, the probability of a random interstellar object aligning near the ecliptic may be small, but we should not overinterpret rarity as evidence of design. Some interpretations of images claim the dust cloud appears to point toward the Sun, something that seems to defy simple solar radiation pressure dynamics. Yet other studies suggest that asymmetric outgassing or geometry of dust release can create features that mimic sunward plumes, especially very early in a comet's inner system approach, or when a body has jet-like surface features. Thus, the feature may not require propulsion or alien alteration. The size estimates of 3I/Atlas have varied, and early reports for very large dimensions have been revised downward. While still large, the uncertainties in size preclude confidently using it as an argument for unusually big, requiring artificial origin. Natural processes can produce large fragments, especially in systems with different histories of collisional grinding and ejection. An often repeated axiom in science, extraordinary claims require extraordinary evidence, looms large in this discussion. Major scientific caution has been voiced, for example, by a SETI-linked paper that responds to the artificial probe claims. The paper notes that 3I/Atlas looks like a comet. It does comet things. The evidence is overwhelmingly pointing to this object being a natural body. The authors stress that while keeping an open mind is wise, there is no compelling signature of artificial origin. No radio signals, no detectable maneuvers, no obvious construction signs. Without such hallmarks, the simplest explanation remains the natural one. Searches for propulsion or communication signatures have so far yielded nothing. Although some have argued that the absence of such signatures is not proof of absence, the lack of any clear evidence shifts the burden of proof heavily toward the hypothesis that this is simply a Voyager rock, albeit an unusual one. In terms of chemistry and dust behavior, many of the oddities of 3I/Atlas have natural analogues, albeit seldom seen in our solar system. For instance, some long-period comets display outgassing from large icy grains at large distances, and some show compositions that differ substantially from typical comets, reflecting the diversity of formation environments. The JWS study on the CO2 dominance suggests a formation in low metallicity or highly irradiated environment rather than a manufactured craft. That it is different is unsurprising for an object from another star. What matters is whether its behavior diverges fundamentally from known physics or composition, and so far it does not, though it skirts the edge. Furthermore, the detection of water at large heliocentric distances may at first seem odd, but other comets have shown early activity due to sublimation of volatile ices or microscopic icy grains in the coma releasing water vapor even before the nucleus warms significantly. Studies show such behavior, though rare, is not unprecedented. Thus, 3I/Atlas could simply reflect an extreme but natural case of interstellar comet chemistry. The polarimetric observations of 3I/Atlas also provide context. Recent polarimetric studies find that the object's polarization phase curve reaches a minimum of -2.7% at small phase angle, unprecedented among known comets or asteroids, yet consistent with some trans-Neptunian objects or centaurs, and thus hinting at a novel but natural type of small body rather than an artificial one. In this sense, the anomaly might mark a new category of interstellar comet rather than proof of alien craft. Activity and outgassing, how 3I/Atlas is behaving. From the earliest observations, it was evident that dust and gas were being released from the nucleus and forming a surrounding cloud. The fact that it was already active so far from the Sun and showing a broad coma suggests a higher level of intrinsic activity. Astronomers have suggested that 3I/Atlas may be significantly larger than previous interstellar objects, giving it a larger fuel reservoir for activity. The early activation and relatively high dust and gas release rates make it a best target yet for studying an interstellar comet's behavior in real time. In terms of how the activity evolves as it approaches perihelion, the expectation is that the volatile release rate will increase, the coma will expand, the tail will lengthen and become more visible, and the dust production may accelerate. Observers are closely watching to see whether 3I/Atlas undergoes outbursts, sudden large increases in brightness, or fragmentation, as some comets do under thermal stress. As of late August, no major fragmentation events had been publicly reported. One factor of interest is how the high inbound velocity interacts with the activity. Because the object is moving rapidly through the inner solar system, the effective time under strong solar heating is shorter than for slower comets. That rapid transit means the heat input on the nucleus changes quickly. The thermal wave moves inward on the nucleus differently, and dust and gas release may behave differently than for comets that spend more time near the Sun. The speed and activity interplay suggests that for 3I/Atlas, the activity window is compressed, meaning that high cadence monitoring is especially important. The appearance of the coma and tail suggests that dust grains may be large and moving relatively slowly, giving the broad, less sharply defined tail, and that some of them may survive longer, indicating different dust grain size distributions than typical. For example, the sun-facing plume may result from large grains ejected preferentially toward the Sun due to thermal wave driving, and those grains linger to form the unusual morphology. Studies have suggested that large grain size and slower sublimation may be at work. Researchers are also exploring non-gravitational accelerations. Comets that outgas strongly can experience slight accelerations beyond the pure gravity of the Sun and planets. Monitoring of 3I/Atlas will look for such accelerations, which can hint at how much mass is lost, how jets are oriented, and how the nucleus might be shaped. One analysis suggests that outgassing should produce measurable non-gravitational effects, and monitoring them will help constrain the physical and internal properties of the nucleus. Overall, the activity and outgassing of 3I/Atlas are providing a rare real-time laboratory of an interstellar object undergoing heating, volatile loss, and dust release. The early activation, relatively high loss rates, coma and tail development, and unusual morphological features all combine to mark 3I/Atlas as a distinctive object, a visitor whose behavior may reflect its foreign origin and unique journey. Determining the size and mass, challenges and uncertainties. Determining the size and mass of 3I/Atlas is surprisingly difficult, even with powerful telescopes, because several factors conspire to obscure the basic parameters. One of the major hurdles is that the nucleus of the object is hidden within its coma and blended with reflected light from dust and sublimated material. The fact that the nucleus cannot currently be resolved directly forces astronomers to estimate size indirectly, often providing only upper or lower limits rather than a precise measurement. Hubble's sharpest images indicate an upper limit on the diameter of about 5.6 kilometers, while the lower bound estimate is as small as 320 meters. These broad bounds reflect the uncertainty inherent in the measurements. The wide range arises because to convert observed brightness into size, one must assume the albedo, which is the reflectivity of the surface, assume how much of the brightness comes from the nucleus versus the surrounding dust, and also assume a shape and orientation, all of which are uncertain. Albedo is one key unknown. If the nucleus or its surface, or the dust coating it, is very dark, reflecting only a small fraction of sunlight, then for a given brightness, the nucleus must be larger to reflect that amount of light. Conversely, if the surface is more reflective, a smaller nucleus can produce the same brightness. In an analysis, scientists assumed a geometric albedo of 0.04 or 4% for the nucleus, which then gave the upper bound of radius, less than 2.8 kilometers, under their model. If the actual albedo were higher or lower, the size estimate would shift accordingly. The measured brightness includes light scattered by the dust cloud as well as the nucleus itself. The dust can inflate the apparent size or brightness of the object, leading to overestimates of the nucleus size if not carefully corrected. For 3I/Atlas, the Hubble team specifically fitted a surface brightness distribution of the inner coma and inferred the nucleus must be smaller than the specified upper limit for their assumed albedo. The same paper notes the nucleus cannot be smaller than 0.16 kilometers radius if the sublimation driver is carbon monoxide, because that minimum size is required to supply the observed dust loss rate. Again, assumptions drive the lower bound. Estimating the mass is even more uncertain. mass requires knowledge of volume and density of the nucleus. With radius uncertainty of, say, between 0.16 kilometers and 2.8 kilometers, the mass estimate can vary by orders of magnitude. One commentary by Avi Loeb sketches a scenario where the diameter might be as large as 46 kilometers, a value others consider unlikely, and computes a corresponding nucleus mass of 10 to the power of 17 kilograms under certain solid density assumptions. But the mainstream Hubble size limits point to the nucleus being much smaller, and dust loss models suggest a modest mass. For instance, another paper computes a dust mass loss rate of about 6 to 60 kilograms per s when the comet was at 3.8 AU. Using that and the expected non-gravitational acceleration, still upper limited, allows derivation of lower mass bounds, but such calculations are highly model dependent. Another difficulty stems from the outgassing and mass shedding itself. Because 3I/Atlas is active, it is losing material, and that alters its motion subtly. In principle, the non-gravitational acceleration caused by outgassing jets can provide constraints on mass. But in practice for this object, the non-gravitational acceleration has not been measured with precision. Instead, only an upper limit is available. Without a well-determined acceleration, using that method to pin down mass is limited. Assumptions about nucleus density vary. Some models assume a typical cometary density of 0.5 to 1.0 g per cubic centimeter, or somewhat less if porous. But if 3I/Atlas has a different internal structure, perhaps higher porosity or different composition or heavy refractory dust content, then the mass estimate could shift further. The result is that any mass number carries large uncertainties. Early size estimates of 10 to 20 kilometers diameter were quoted in the media shortly after discovery, but then the estimates were revised downward sharply. That historical revision underscores how initial size estimates can be highly speculative and subject to refinement. Measurement of the dust and gas production rates also feed into size-mass estimates. If one assumed a steady loss rate and modeled lifetime, one might infer lower bounds on nucleus mass. But the assumptions about particle size distribution, dust speeds, and sublimation physics add large uncertainty. If all this wasn't complicated enough, the orientation and shape of the nucleus are unknown. If the nucleus is elongated or irregular, the cross-section seen may vary with rotation and viewing angle, affecting brightness measurements and thus size estimates. Rotational variability or jets may also modulate brightness, adding noise to size inference. At present, there has been no reliable measurement of rotational period. Light curves are dominated by the coma photons. That absence of a known rotational state adds another layer of uncertainty. If large grains are ejected and linger near the nucleus, they may contribute significant reflected light or thermal emission that is then attributed, erroneously, to the nucleus. Some of the morphological work notes that 3I/Atlas displays a sun-facing dust plume and broad coma, meaning that some portion of brightness is almost certainly due to dust rather than the solid nucleus alone. Without isolating the nucleus contribution, size estimates remain upper limits. Origin and age. Where might 3I/Atlas have come from? The journey of 3I/Atlas begins far beyond the boundaries of our solar system. The observations and orbital data together point to an origin in another star system and suggest that this interstellar visitor has traversed our galaxy for billions of years before arriving here. A number of strands of evidence converge to shape our understanding of its origin and age. Firstly, the direction from which 3I/Atlas approached the Sun tells part of its story. According to the NASA fact page, 3I/Atlas entered from the general direction of the constellation Sagittarius, near the galactic center region. Its motion, when traced backward, does not correspond to the typical heliocentric direction associated with comets from the Oort cloud or Kuiper belt. Instead, the trajectory has a steep inclination and a velocity vector that suggests the object has been traveling through the galactic environment well beyond our Sun's immediate neighborhood. One summary states that the direction of 3I/Atlas's arrival is steep and lies well off the solar apex, hinting at a completely different region of the Milky Way. Secondly, the kinematic parameters, including the hyperbolic excess velocity and orbit inclination, further support that 3I/Atlas was ejected from its parent system long ago and has drifted in interstellar space. Since the object's orbit is unbound, eccentricity well above 1, it must have been imparted with sufficient energy at ejection to escape its home star's gravity and then traverse the galaxy before passing through our solar system. The fact that no close encounter with our planets could have given it that energy underscores that its birthplace lies elsewhere. This strongly suggests a foreign origin. Thirdly, recent studies attempt to place age estimates on 3I/Atlas based on its membership in a galactic population. One research highlight notes that this object appears to belong to the Milky Way's thick disk population, a component of the galaxy dominated by very old stars, generally metal-poor compared to the thin disk. In that context, one paper estimates a plausible age of 7.6 billion to 14 billion years, under the assumption that the object formed in the thick disk, which is older than our Sun's 4.6 billion year age. Other estimates suggest a range of 3 to 11 billion years, depending on assumptions about ejection timing, stellar encounters, and galactic mixing. If 3I/Atlas indeed formed in the thick disk, this places its origin in a region of the galaxy where star formation largely ceased many billions of years ago, meaning this object may be among the oldest comets ever studied. One Science Radio interview notes that it could be the oldest comet yet seen. The idea is that the parent star may have belonged to a generation of early galactic objects, ejected its small bodies early in its lifetime, and left them to roam the interstellar medium for eons. Regarding possible parent stars, no definitive star has been identified as the source of 3I/Atlas. Because it has likely spent a long time traveling, its position and path have been perturbed by galactic tides, star encounters, and other dynamical processes, making backward tracing challenging. According to the Wikipedia summary, although one study found that 3I/Atlas may have passed within 1 parsec of 25 known stars over the past 10 million years, this is not enough to pinpoint a parent. The vast timescales and the mixing of stellar populations mean that the specific system from which it was ejected remains unknown. In terms of ejection mechanics, models of planetary system formation and small body dynamics suggest that objects like 3I/Atlas may be ejected by gravitational interactions. For example, a young star's protoplanetary disk interacting with giant planets or close stellar flybys early in the system's history. Once ejected, the body travels through interstellar space, potentially for billions of years. One review article notes that small bodies may escape into interstellar space at any time, leaked from extrasolar Oort clouds, or ejected following close encounters. The CO2-rich composition of 3I/Atlas, covered in earlier sections, further suggests a formation in a cold region far from its parent star, perhaps beyond the carbon dioxide ice line of its original system. The environment may have been significantly different from our solar systems, implying a greater variety of compositional outcomes in the galaxy. This directly ties into origin scenarios. Once we consider age, origin, and composition together, 3I/Atlas becomes more than just a visitor. It becomes a historic sample of galactic material. If it formed in a primordial system, far older than our Sun, its ice and rock may have preserved features of early planetary system environments, unmodified by repeated solar heating. The idea is that it acted as a time capsule, carrying within it the conditions of a distant system's youth. One article states that because it likely formed in the thick disk, it should be rich in water ice compared to objects from later epoch systems. It bears noting, however, that while these origin and age models are compelling, they remain speculative in many respects. Because we lack a resolved parent system, exact ejection timing, and full dynamical history, our conclusions are probabilistic. For example, If the object formed in the thin disk instead of the thick disk, the age estimate might be lower. Models must account for ejection speed, stellar encounters, and how travel time within the galaxy dilutes origin signatures. Nevertheless, the bulk of current evidence favors a very old age and a birthplace in a remote and ancient region of the Milky Way. In the context of planetary science, this origin story magnifies the value of 3I/Atlas. We are not just watching a comet from another star system, we are observing a relic that may predate our Sun and provide direct clues about planetesimal formation in early galactic environments. Its composition, trajectory, and structural features combine to make it a probe of other star systems' histories. Researchers continue to monitor the object as it approaches perihelion and then recedes, using each piece of data to refine its origin narrative. Observational programs spanning from ground-based telescopes to space observatories are sharpening our understanding of how this visitor ties into the broader galactic context. In doing so, 3I/Atlas may help answer profound questions. How common are planet-building processes in the galaxy? How variable are the conditions under which icy small bodies form? What does the distribution of ejected bodies tell us about the architecture of planetary systems beyond our own? What 3I/Atlas can tell us about other planetary systems? Our models for planetary formation anticipate that early in a system's life, interactions among giant planets or stellar flybys can scatter outer icy bodies into interstellar space. The very fact that 3I/Atlas arrived here suggests that our galaxy contains vast numbers of such wanderers. Each interstellar object is a messenger of how planetary systems evolve dynamically and how material from one system may be exchanged or scattered into the galaxy. Because 3I/Atlas has been drifting for perhaps billions of years, it serves as a temporal time capsule anchored in its parent system's earliest epoch. It could be 3 or more billion years older than our Sun. By studying a body that formed in a chemically different era of the galaxy, we may glimpse what planet building looked like under conditions unknown in our system. Perhaps lower metallicity, less stellar irradiation, or different initial disk compositions. These data help calibrate how planetary systems might differ by stellar environment and age. Because 3I/Atlas reached our neighborhood from towards the galactic center region, and with unusually high velocity, it suggests origins in a dynamic part of the galaxy, possibly one less sampled by our solar system's local inventory. That highlights the idea that planetary systems are not all aligned or neatly arranged like our own. This also makes it possibly the oldest known comet. As we compare its physical and chemical traits with ours, 3I/Atlas could refine our understanding of habitability, volatile delivery, and planetary architectures. For example, if many planetary systems produce comets with higher CO2 abundances, then the delivery of water to inner planets may follow different patterns than ours. The idea that water might not dominate icy bodies elsewhere means that planets formed in those systems could have very different volatile histories. As an interstellar field sample, 3I/Atlas underscores that Earth's volatile origin story may not be typical. The study of 3I/Atlas also has implications for planet formation theory. For instance, the presence of dust, gas, and large grains in its coma suggests that planetesimal formation and retention of volatiles remained efficient in its parent system. The early activation of the comet hints at abundant volatile ices in surface layers, something perhaps associated with formation beyond a CO2 ice line in a protoplanetary disk. That difference in formation locale within the parent system could translate to a different architecture of planets, such as more distant icy planetesimals, more massive outer belts, different migration patterns. By evaluating its dust-to-gas ratio, outgassing drivers, morphology, and kinematics, scientists are effectively reading a report from a remote star system, one that we cannot visit, but whose materials we can inspect. Lessons learned here will influence how we interpret debris disks, exoplanet systems, and the origin of volatiles on planets. The object is a bridge between solar system science and exoplanetary science, helping to integrate these fields. Every grain of dust we analyze, every molecule we detect, every orbital parameter we compute helps us position our solar system within the vast tapestry of planetary systems in the Milky Way. Potential threat to Earth, assessing collision risk. When it comes to evaluating whether 3I/Atlas might pose a threat to Earth, the observational evidence consistently shows that the object remains well outside the realm of collision risk. According to the data published by NASA, this interstellar visitor will not come any closer than approximately 1.8 AU to Earth. That is roughly equivalent to about 270 million kilometers, a substantial buffer far beyond the distances at which objects are considered hazardous. The determination of that minimum approach distance arises from the orbital solution computed soon after its discovery. Because of its hyperbolic path, the object's trajectory does not cross Earth's orbit in the way that many near-Earth asteroids or periodic comets might. Detailed orbit tracking and astrometry allowed astronomers to trace backwards and forwards 3I/Atlas's path and determine that its closest Earth approach is forecast for about the 19th of December 2025 at the distance of 1.797 AU or 269 million kilometers. That calculation includes allowance for uncertainties, and the margin remains large, by orders of magnitude beyond the distance that would normally trigger impact concerns. In the context of planetary defense frameworks, key parameters include the magnitude of approach distance, the speed of the object, and the likelihood of gravitational or non-gravitational perturbations altering its path toward Earth. For 3I/Atlas, all these factors lean strongly towards no threat. The comet travels at very high speed and on a retrograde, steeply inclined orbit. That high speed, coupled with a trajectory that does not intersect Earth's orbital plane at close range, undercuts any credible scenario of imminent collision. Moreover, the closest passage distances of 3I/Atlas relative to other planetary orbits further support its safe passage. For instance, the object will pass near the orbit of Mars, but even that close approach is at about 0.18 to 0.20 AU, or about 27 to 30 million kilometers, from Mars's path, not from Mars itself, thereby indicating that the object is not threading deeply into planetary crossing zones. That means it is unlikely to experience strong perturbations from planetary gravity that might redirect it into an Earth impact trajectory. There is the question of how uncertainties in orbit and outgassing might affect predictions. Comets can exhibit non-gravitational accelerations due to jets, sublimation, or asymmetric outgassing. Such forces can shift trajectories slightly, but for 3I/Atlas, the predicted margin of approach to Earth is so large that even if moderate non-gravitational influences occurred, they would not move it from safe passage to danger zone. The documented statement from NASA notes that the object poses no threat to Earth. It's worth emphasizing that although 3I/Atlas is safe, its case underscores how interstellar objects might challenge planetary defense thinking. Because they arrive at high velocities, from unusual directions, sometimes with poorly constrained properties, each represents a wild card. The early detection of 3I/Atlas allowed orbit refinement and threat assessment. Without such detection timing, a late arrival could reduce warning time and raise the challenge of assessing potential hazard. The hazard posed by any object is a function of size, speed, and impact probability. If by some miracle an interstellar object were on a direct Earth impact path, the high velocity would increase kinetic energy significantly compared to slower solar system comets of the same size. While this increases potential severity, it does not apply in 3I/Atlas's case because it is not on a direct path to Earth. In practical terms, what this means is that observers and planetary defense agencies treat 3I/Atlas as a scientific opportunity, not a threat. Observation campaigns are monitoring its coma, trail, dust, gas release, orbit refinement, and possible spacecraft observational windows. but there is no need for hazard mitigation measures such as deflection or emergency response. The margin of safety is well established. Yet the review of 3I/Atlas does feed into longer-term planning for planetary defense. While this object is safe, future interstellar visitors might not be. Models suggest that the Milky Way may host many objects ejected from other star systems. Though rare, an interstellar object on an Earth-crossing trajectory, even if unlikely, could arrive at high speed and from a direction not covered by typical surveys. That means surveillance systems must be capable of detecting high-inclination, retrograde, high-velocity objects. The detection of 3I/Atlas demonstrates that such systems are operating and can spot these visitors early enough to assess hazard. Could humanity defend against a threat? Like 3I/Atlas, how likely are interstellar objects to pose a hazard? Because their numbers are uncertain and their properties variable, this remains a point of scientific and practical risk assessment. Even if rare, the consequences of an impact from a sufficiently large interstellar body would follow the same laws of physics as a solar system impact. Yet, the difference in source, speed, and composition may amplify or alter effects. The long tail of unknown unknowns means risk models must include interstellar visitors as a special case. Planetary defense traditionally emphasizes size, mass, composition, orbit, and impact probability. But for interstellar objects, the unknowns multiply. Density and composition might differ markedly. Internal structure could be unusual, and the breakdown behavior may diverge. For example, if an interstellar object has a higher velocity relative to Earth, it may present different fragmentation patterns on atmospheric entry. Risk models need to account for such variations, adjusting estimates of damage footprints, airburst energies, and fragment dispersion accordingly. The inclusion of interstellar objects also implies we might need new classification and alert scales. The established Torino and Palermo scales are designed for near-Earth objects with repeating orbits and known trajectories. Some researchers suggest a separate interstellar hazard scale, or an extension of existing ones to cover hyperbolic intruders. In a Medium article, Loeb proposed an alert system, in the spirit of the Richter scale for earthquakes, with interstellar objects mapped on a scale from natural 0 to potentially artificial 10. Such a framework would enable nations and researchers to assess and communicate interstellar threats transparently. Higher entry speeds increase kinetic energy exponentially, potentially altering fragmentation altitude and surface damage profiles. The altitude at which an object breaks up in the atmosphere, the shockwave production, and ground effects would differ from typical NEO entries. Models must incorporate variables specific to interstellar intruders, including irregular composition or structural integrity, unknown from solar system analogues. The possibility of defending against an interstellar object, should it ever pose a threat, is a complex and multifaceted challenge. At the heart of planetary defense lies the concept of detection. For any object, especially one traveling from outside our solar system, the sooner we detect it, the more time we have to devise and execute a defense plan. The earlier an object is spotted, the more accurate we can be in determining its trajectory and calculating the potential risk. With an interstellar object moving at far greater speeds than typical solar system comets or asteroids, the window of opportunity for intervention becomes significantly smaller. While detection methods such as ATLAS, PAN-STARRS, and other sky surveys have made great strides in spotting objects coming from within the solar system, interstellar objects remain harder to track and predict. Their high velocity, atypical trajectories, and shorter observation windows make them more difficult to spot early on. This presents a key hurdle. Detection must occur early enough to provide the necessary lead time to act. 3I/Atlas is considerably faster than typical solar system comets or asteroids, which generally move at speeds of around 20 to 30 km per s. The higher speed not only reduces the time available to intercept or alter the object's trajectory, but it also increases the kinetic energy involved in any potential collision. If a collision were to occur with an interstellar object traveling at this velocity, the impact would be far more catastrophic than one from a slower moving object, as the energy involved would be exponentially greater. High-speed impacts introduce the question of whether our current mitigation techniques, such as kinetic impactors, could even be effective at all. One of the main methods currently considered for planetary defense is the use of kinetic impactors, spacecraft that deliberately crash into an object to change its speed and trajectory. In the case of an interstellar object, this would require very precise targeting and coordination. The key problem with kinetic impactors, however, is that they depend on the object being large enough for a significant change in its course to occur. The higher the velocity of the object, the more difficult it becomes to apply enough force to shift its trajectory meaningfully. This means that while kinetic impactors have shown promise in recent tests with smaller, slower-moving asteroids, the same technique might be far less effective against an interstellar object like 3I/Atlas, which is moving much faster and is likely much larger. Another potential defense method is nuclear deflection, which involves detonating a nuclear device near the object to vaporize part of its surface and create a thrust that could change its course. While this method has the potential to work on larger, faster-moving objects, it carries with it a host of challenges. The use of nuclear weapons in space is fraught with technical, political, and environmental concerns. A nuclear detonation could potentially break the object into smaller fragments, each of which might still be hazardous, and depending on where the object is, it could also have unintended consequences for space-based infrastructure or the Earth's atmosphere. The idea of using nuclear devices to mitigate a planetary-scale threat is still largely theoretical and has yet to be tested in real-world conditions. Another intriguing possibility is the concept of laser ablation. In this approach, high-powered lasers would target an interstellar object to heat up its surface, causing it to release material in a process similar to rocket propulsion, altering the object's trajectory. This technique has the advantage of not requiring a physical spacecraft to intercept the object, but it also faces significant technical challenges. The power required to make even the smallest change in the trajectory of an object traveling at interstellar speeds would be enormous, and the technology to achieve this level of precision and power is still far from ready. The energy requirements are so great that current laser technology would not be sufficient to handle the task, especially at the distance an interstellar object might be at when first detected. Given the high speeds, unpredictable orbits, and the vast distances involved, time becomes one of the most critical factors in defending against an interstellar object. If humanity were to ever face an interstellar threat, we would need to detect the object years or even decades in advance to mount any sort of meaningful defense. This is one of the main reasons why planetary defense systems are still in their infancy when it comes to interstellar objects. While we have mechanisms in place to monitor objects within our solar system, interstellar objects are still very much in the realm of unknowns, with systems not yet capable of accurately predicting their trajectories far enough in advance to alter their course. The global coordination of any planetary defense effort is another significant factor. If an interstellar object were to be detected and deemed a potential threat, the response would likely require international collaboration. Such a collaboration would need to include cooperation on a technical level, as well as political considerations. The use of nuclear devices in space, for example, could raise serious legal and ethical concerns, especially given the international treaties that govern space and weaponization. A global threat, such as an interstellar collision, would require a united response, drawing on the expertise and resources of multiple nations, space agencies, and private organizations. Given the unprecedented nature of such a threat, international coordination would be vital to ensure that the correct course of action is taken. In light of all these challenges, it is clear that humanity would be unprepared to face an interstellar object like 3I/Atlas if it were on a collision course with Earth. The technological gaps, time constraints, and political complexities are vast. However, the study of interstellar objects provides a valuable opportunity to prepare for the future. By improving detection systems, refining the models used to predict object trajectories, and developing new defense technologies, humanity can gradually build the capabilities needed to respond to future threats. This ongoing research is not just about defending against one particular object. It is about developing a broader planetary defense infrastructure that can protect the Earth from the unpredictable threats posed by objects from beyond our solar system. Just as the detection and deflection of near-Earth objects have evolved over the years, so too will our capacity to deal with the unknowns posed by interstellar objects, should the need arise. When will 3I/Atlas leave the solar system? What's its future path? The object's exit from the solar system is anticipated to occur in 2026, after passing closest to the Sun on the 29th of October 2025, which is its perihelion. 3I/Atlas will begin its escape from the solar system, traveling ever faster as it moves away from the Sun's gravitational influence. The comet will remain observable for a while, as telescopes will continue to track its path even after it has passed its closest point to the Sun. However, as 3I/Atlas moves further away from the Sun, it will become increasingly difficult to observe. The object will begin to fade from view due to the decreasing amount of sunlight it reflects and the growing distance between it and Earth. Astronomers will continue tracking it for as long as it remains within reach of current observational technology. But by the time it reaches the outer edges of the solar system, the comet will be lost to all but the most sensitive instruments. The final observations will likely occur in the early part of 2026, marking the last days of 3I/Atlas's visibility. After 2026, the comet's path will take it out into interstellar space. The precise future path of 3I/Atlas, while understood in broad terms, is difficult to predict with exactitude because of the complexities of its hyperbolic trajectory and its non-gravitational behavior, which can slightly alter its motion as it moves through the space surrounding the Sun. Depending on its precise path, 3I/Atlas could eventually come close to another star system, but it will not remain bound to any star in particular. 3I/Atlas will never return to visit again. Its hyperbolic orbit ensures that once it leaves, it will never loop back. The future journey of 3I/Atlas will take it deep into the interstellar medium, where it will pass through regions of space sparsely populated with matter. Its trajectory may take it through various interstellar clouds, but it will remain a lone wanderer, unanchored by any star. The object will be subject to the forces of the galaxy's gravitational fields, but its path will be dictated by the same mechanics that govern all objects escaping the Sun's influence, a mix of inertia and gravitational interactions. While 3I/Atlas will eventually travel millions of light-years away from our Sun, the possibility of future encounters with other stellar systems remains, though highly unlikely given the vast distances involved. As it continues on its journey, it will carry with it clues about the regions it came from and the processes that shaped it. It will remain, in essence, a probe of the greater cosmos, a messenger from another star system. The legacy of 3I/Atlas's brief sojourn will live on in the data it has provided, helping to fuel the future study of interstellar objects and refine our understanding of the broader cosmos. Possibility of a probe to catch up. Could we mission to 3I/Atlas? The concept of capturing an interstellar object and sending a probe to observe it in detail is an idea that has intrigued scientists and space enthusiasts alike. However, such a mission, while theoretically possible, would face a daunting array of technical challenges. The most significant of these challenges are the high relative velocity between Earth and 3I/Atlas, the narrow time window for intercepting it, the extreme fuel and energy demands, and the need for an advanced trajectory design. Together, these factors make the idea of a mission to intercept 3I/Atlas an extraordinary technical undertaking, one that would stretch current space exploration capabilities to their limits. At the core of this challenge lies the relative velocity between 3I/Atlas and Earth. This high velocity means that even if a spacecraft were launched to intercept 3I/Atlas, it would need to travel at speeds far beyond what current propulsion technologies can achieve. In fact, to match 3I/Atlas's speed, a spacecraft would need to accelerate at a rate that would be technically unfeasible with today's chemical rockets. The speed of 3I/Atlas effectively means that the spacecraft would have to be able to achieve a delta V of an enormous magnitude, which represents one of the most significant obstacles to such a mission. The concept of delta V is central to any space mission, as it quantifies the amount of velocity change a spacecraft needs to achieve in order to reach a given target. To match the speed of 3I/Atlas, a spacecraft would need to accelerate at an incredibly high rate in order to catch up with the object. Even with highly efficient propulsion systems, such as ion drives or nuclear thermal propulsion, the energy required to accelerate a spacecraft to the necessary speed would be immense. Current space missions rely on chemical propulsion, which, while effective for launching objects into space, has limited efficiency when it comes to high-speed rendezvous missions. While ion drives, which offer much better fuel efficiency, are more suitable for deep space exploration, they still lack the power needed for high-speed interception of a fast-moving object, like 3I/Atlas. The narrow time window for launching a mission to catch up with 3I/Atlas also presents a significant challenge. Once 3I/Atlas has passed its perihelion, it will begin moving away from the Sun at an accelerating pace, meaning that the window for interception will rapidly shrink. The timing of the launch would need to be almost perfect. A spacecraft would have to be launched at exactly the right moment to catch up with the object while it is still within reach. Any delay in the launch would result in the spacecraft missing the object entirely, as 3I/Atlas would be too far out of reach by the time the spacecraft arrived. This makes planning such a mission highly challenging, requiring advanced predictions of the object's path and precise calculations of the launch window. Even if a spacecraft were able to reach 3I/Atlas, there would still be the question of the trajectory required for such a mission. To catch up with an object moving so rapidly, the spacecraft would need to execute a carefully calculated gravity assist maneuver to boost its velocity. A gravity assist is a technique in which a spacecraft uses the gravity of a planet or another celestial body to slingshot itself and gain speed, effectively borrowing velocity from the planet to increase its own. For a mission to intercept 3I/Atlas, the spacecraft would need to pass close enough to a planet or body within the solar system to increase its velocity without using excessive fuel. This maneuver would need to be precisely timed and planned, and even then, the spacecraft would still need to overcome the immense challenges posed by the object's high relative speed. The spacecraft would not only need to reach the object, but it would also need to be able to slow down, match its speed, and enter a trajectory that would allow it to closely observe the object. Fuel consumption is a critical consideration for space missions, especially when considering the high speeds involved in a mission to intercept an object moving at interstellar velocities. The energy required to alter the spacecraft's trajectory and speed would be monumental, and the spacecraft would likely require an entirely new class of propulsion system to handle such a task. Additionally, the spacecraft would need to be equipped with sophisticated navigation and communication systems capable of performing long-duration operations. A mission to intercept an interstellar object would likely take many years to complete, and during this time, the spacecraft would need to be able to make real-time adjustments to its course. Advanced AI and autonomous systems would be required to handle these adjustments, as manual control from Earth would not be feasible given the communication delays and the distance the spacecraft would be traveling. The spacecraft would also need a robust power source capable of sustaining it through such an extended mission, possibly relying on nuclear power sources or advanced solar arrays that could function even at the vast distances from the Sun. Proposals for such a mission do exist, though they are still in the realm of theoretical ideas. One such proposal is the idea of a chasing spacecraft. Such a mission would likely involve a slow, gradual build-up of velocity over time using highly efficient ion engines or even nuclear propulsion systems, both of which offer far greater efficiency than traditional chemical rockets. The spacecraft would need to perform gravity-assist maneuvers using the gas giants of the solar system, such as Jupiter or Saturn, to gradually increase its velocity and reach the speeds necessary. While such a mission is still hypothetical, it represents the kind of mission that might one day be possible with the necessary advances in propulsion, navigation, and communication technology. Should humanity develop the technology to catch up with an interstellar object, what could we learn from such an encounter? The scientific value of studying an interstellar object up close would be immense. It would provide an unprecedented opportunity to study the composition, structure, and behavior of an object from another star system. Understanding the materials and gases present in such objects could provide critical clues about the formation of our own solar system and the wider galactic environment. It could even help inform our understanding of how life might arise in other star systems by revealing the building blocks of organic materials that might be present in such distant regions of space. The high relative velocity, narrow time windows, and immense fuel and energy demands make it unlikely that we could launch such a mission in the near future. However, the ongoing advancements in space propulsion, AI, and navigation systems may one day make such missions feasible. For now, 3I/Atlas only serves as an important reminder of the challenges and possibilities of interstellar exploration, inspiring future generations to dream of reaching out beyond the confines of our solar system. What we know of its host, star or formation environment. Efforts to identify the actual parent star or planetary system from which 3I/Atlas was ejected are underway. One key study by researchers from the Shanghai Jiao Tong University used data from the Gaia satellite along with galactic orbital integration to trace potential close encounters between 3I/Atlas and known stars. The scientists, led by Yiyang Guo, found 25 stars whose positions and motions might have brought them within about 1 parsec of the object in the past, but none appear to be plausible hosts under conventional ejection mechanisms. Many of those encounters involved relative speeds above 20 km per s, which is high for an object being gently ejected from a star system. The strongest encounter detected involved a wide M-dwarf binary about 1.64 million years ago, at a closest approach of about 0.242 parsec. But the encounter speed was 28.39 kms, again too high for a classical ejection from a planetary system. The result? Astronomers currently conclude that a direct association with a specific star is unlikely, which leaves 3I/Atlas drifting unsourced among the stars. Though we cannot yet pin the origin star, the kinematics of 3I/Atlas suggest it likely originated in the Milky Way's thin disk population of stars. The thin disk is the region of the galaxy where our Sun resides, with moderate metallicity and a large number of stars. The study by Guo reported a posterior probability of over 96% for a thin disk origin based on the object's velocity vector and galactic coordinates. This is important because it suggests that 3I/Atlas did not come from some exotic old metal-poor halo star, but from a more ordinary part of the galaxy, though ordinary by stellar standards still implies a complex, dynamic environment. Turning to its formation environment, observations of 3I/Atlas's coma give clues about where it might have originated and the conditions it experienced. The measured CO2-H2O ratio of 8 is among the highest ever recorded in a cometary body. This suggests the nucleus of 3I/Atlas may have formed in a cold region of its parent protoplanetary disk. Such a chemistry implies formation under different conditions than most comets in our solar system, and it invites consideration of its parent system, being different in temperature, radiation flux, or chemical composition. In addition, modelling by a team out of the University of Oxford placed the likely age of the object at more than 7.6 billion years, with a suggestion that it might even be as old as 14 billion years, older than our own solar system. If so, 3I/Atlas could have formed around a star in the early galaxy, perhaps when the metallicity of stars was lower and the cosmic environment more intense. That could explain its unusual volatile inventory and perhaps its size or structural robustness if it survived billions of years in interstellar space. Given that the object has been drifting for so long, galactic dynamics complicate identification of its birthplace. Over millions or billions of years, gravitational perturbations from passing stars, giant molecular clouds, and gas drag alter trajectories. In the case of 3I/Atlas, the Guo study found that the cumulative influence of known stellar encounters on its speed and direction is weak, suggesting that the object retained much of its original velocity vector. However, even so, the backward path is smeared by uncertainties in the gravitational potential, unknown past interactions, and the fact that we lack full velocity and position history for the object and for many stars. So, any attempt to trace back to a particular star must cope with large uncertainty. The longer the journey, the more the trail is blurred. The direction of arrival is intriguing because that region points toward the galactic center and also lies in the southern hemisphere of the celestial sphere. Many early detection efforts of interstellar objects were biased toward the northern sky, so the discovery of 3I/Atlas coming from the south tells us that the survey volume for such objects may be larger than previously believed. More broadly, the fact that its incoming path is nearly aligned with the ecliptic plane of our solar system means it pierced the plane of planetary orbits in a way that made it easier for us to detect. That alignment doesn't guarantee a host star, but it does suggest that the object may have entered our solar system through a sweet spot, where observation and detection are more favorable. The CO2 dominance might mean the parent system lacked abundant water, or that the object spent so long exposed to cosmic rays and solar radiation that its more volatile ices were depleted. The presence of water, Colorado, and OCS in smaller amounts means that the nucleus is not inert. It retains icy materials despite its long interstellar travel. The picture that emerges is one of a body formed in a cold, possibly remote region of its system, ejected perhaps by giant planet scattering or stellar flyby, then wandering for eons until it encountered the Sun's gravity. The idea of an interstellar object coming from a star system billions of years old and billions of light years across makes clear how rare and precious the data are. Each measurement of the trajectory, each spectral line in the coma, each photometric reading of its brightness opens a window into a region of the galaxy we cannot otherwise access. Even without locating the exact source star, the fact that the object carries the chemical and dynamical fingerprint of its birthplace is profoundly valuable. Tracing back farther, studies of interstellar object populations, such as the Otautahi-Oxford model, place 3I/Atlas within expectations of interstellar debris interacting with the galaxy's potential fields. Matthew Hopkins, from the Oxford study, showed that 3I/Atlas's velocity and radiant are consistent with an object that formed in the galactic disk and has been wandering for a large fraction of the age of the Milky Way. That supports the notion that what we are witnessing is not just a local oddity, but a representative of the broader population of material ejected from countless planetary systems across the galaxy. If the object formed far from its star and near the CO2 ice line, then its parent system may have had massive outer planets or a dynamically active early stage that flung planetesimals outward. The ejection could have occurred during a phase of planetary migration, stellar flyby, or close encounter, a process that our own solar system may have experienced in its early history. The composition and trajectory of 3I/Atlas suggest we may be seeing the product of that process in action, albeit in extreme form. While the inability to trace a direct home star means we cannot yet say this is where it came from, the evidence strongly guides us toward a likely region. A star in the galactic thin disk, relatively old, probably low in heavy element content compared to younger stars, with a protoplanetary disk cold enough to allow CO2 ice to form and remain until ejection. The long travel time means that by now that parent star might have moved significantly and the path of the object may have changed slightly, but the core information embedded in its chemistry and motion remains. As research continues, future surveys and more advanced Gaia data releases may help refine the list of possible parent stars, perhaps narrowing candidates or even offering a direct identification. Implications for astrobiology. One of the big questions is how common organic molecules and volatile ingredients for life are in the galaxy and how they move between systems. Comets in our solar system are considered potential delivery vehicles of organics, water, and other volatiles to early Earth or other planets. An interstellar object like 3I/Atlas might carry organics or volatiles formed in a totally different environment. If its coma or dust includes carbon-rich compounds, complex organics or isotopic signatures, different from solar system norms, that tells us new things about how life-enabling chemistry might be spread across the galaxy. The detection of water at large heliocentric distances, in 3I/Atlas's case via hydroxyl emissions at 3.5 AU, comparable to 40 kilograms per S of water loss far from the Sun, raises the possibility that icy bodies ejected from other systems might persist long enough and travel far enough to seed material in other systems. The concept of panspermia, the idea that life or prebiotic chemistry might move between star systems via asteroids or comets, gains a real observational meter here if objects like 3I/Atlas are common, and if they retain volatiles and organics during their interstellar journey, they might act as probes of galactic chemical exchange. Each such object could carry the fingerprint of its birth environment, and by studying it, we can begin to map how ingredients for life are distributed on a galactic scale. Whether 3I/Atlas actually carries complex organics remains unknown, but the mere fact that we have a foreign body to study offers that possibility. Another implication is how we understand the diversity of planetary systems. Historically, we built models of planet formation and evolution based on the solar system because that is all we had. Interstellar visitors begin to challenge whether our solar system is typical or atypical. If many interstellar objects turn out to have compositions or dynamical histories very different from ours, we may need to broaden our conception of planet formation to include low metallicity disks, high radiation environments, different ice lines, heavy bombardment histories far more intense than ours, and ejection processes that vary across galactic epochs. In planetary science, there is also the specific question of what happens to small bodies before, during, and after ejection. The survival of 3I/Atlas in interstellar space for potentially billions of years means that planetesimals may remain intact long after their system of origin decays. That has implications for debris disk lifetimes, for our estimates of how many planetesimal systems produce, and for how interstellar space accumulates and delivers such bodies. The ability of such an object to retain volatiles, to show comet-like activity when warmed by a new star, suggests that ejection does not necessarily destroy all signs of history. Astrobiologically, the fact that 3I/Atlas exhibits comet-like activity also means that planetary systems that eject icy material may seed their surroundings. If that material crosses into another system, or if it passes close to another star and its planets, the potential exists for cross-pollination of material. While speculative, this raises the possibility of a gentle form of interstellar exchange of building blocks. Whether or not it awakened life elsewhere is unknown, but by studying it, we learn how far planetary systems reach, how their dust and ice may spread, and how cosmically connected systems may be. The study of 3I/Atlas underlines the need for rapid response observatories capable of detecting and characterizing interstellar objects. The paradigms of planetary science are expanding to include foreign system material as a separate class. Through astrobiology, it widens the notion of the habitable system to one where material from one system can influence another. While we often think of planets and life developing in isolation, the existence of interstellar objects invites the notion that the cosmic neighborhood is dynamic, with matter crossing between stars, sharing chemical stories and perhaps even biological potential. The paradigm shifts from our system formed and evolved alone toward our system forms part of a network of systems with debris, ice, dust, and possibly organics moving between them. We learn more about our own system when we have an outsider to compare. If our comets are rich in water but 3I/Atlas is rich in CO2, what does that tell us about the uniqueness of Earth's water inventory? If objects from other systems carry different volatile profiles, then perhaps the prevalence of water-rich planets or habitable zones is more variable than expected. If the delivery of organics is system-specific, the distribution of life-friendly environments might be patchier, but potentially more widespread in unexpected regions. Strategies to intercept future interstellar objects. A key element is the improvement of survey capability. The forthcoming Vera C. Rubin Observatory, conducting its legacy survey of space and time, or LSST, is expected to greatly increase the detection rate of interstellar objects, or ISOs, perhaps from one every few years to several per year. With more timely detections, mission planners will have more lead time to consider intercept trajectories. Complementing LSST, infrared survey missions such as NEO Surveyor will help catalogue faint, high-velocity objects entering our inner solar system. Together, these systems increase the portfolio of potential targets and reduce the surprise factor, which has dogged previous encounters. Once a detection is made, rapid coordinated response is critical. That suggests we need operational mission architecture ready to go. Spacecraft that can launch quickly or are already on standby in parking orbits conducive to intercept. Studies such as those by Southwest Research Institute have modeled spacecraft flybys of objects like 3I/Atlas, showing that for accessible trajectories, the technology exists if the launch window is favorable. One concept envisions a build and wait model. Spacecraft are developed and placed in standby mode, perhaps in Earth orbit or at a Sun-Earth Lagrange point, ready to depart once an ISO is discovered. For example, analysis shows that placing a spacecraft near 1 AU distance from the Sun, close to Earth's orbit, maximizes the chance of intercepting an ISO crossing the ecliptic plane. The standby spacecraft idea might involve placing one or more small spacecraft in high readiness, either in Earth orbit or in heliocentric orbit near Earth's path. Once an ISO is identified, the spacecraft would be directed to perform a fast burn and set off on an intercept trajectory. Building such a capability requires not only ready-to-fly spacecraft, but also launch infrastructure in rapid response mode, with fuel and trajectory flexibility accounted for. Some mission architecture studies suggest that with Earth-based standby craft, response times of days to weeks might be feasible, though the technical, logistical, and cost factors remain challenging. Another strategic aspect is intercept readiness. Missions need generic payloads designed for fast flyby science rather than slow orbital insertion. The hyperbolic speed of many ISOs, tens of kilometers per second relative to the Sun, means that orbiting the object may not be feasible. Instead, a high-velocity flyby with a camera suite, dust and gas spectrometer, possibly a guided impactor or dust collector, is the most realistic near-term approach. Studies suggest that even if we cannot slow down to match the ISO's speed, a dedicated flyby mission could collect data on composition, structure and volatile release and return that to Earth. Coordination between ground and space-based observatories is integral to mission success. Early detection by optical and infrared surveys allows preliminary orbit determination and composition hints. This in turn triggers spacecraft decision-making, whether to launch, intercept, or continue remote study. The data that ground and space telescopes collect feed mission design by refining velocities, delta-V requirements, and hazard assessment. Mission planners can then assess whether an intercept is viable and begin operations to target the object before it exits the inner solar system. The survey-to-mission pipeline must be tight and fast. a delay of even a few weeks can mean that the object is too far out, too fast, or in a position unsuited to spacecraft rendezvous. One of the most talked about missions that embodies this readiness concept is the Comet Interceptor, a mission by the ESA and JAXA planned to launch in 2029 and wait at the Sun-Earth L2 point for a suitable target, possibly an interstellar object. The craft is designed with electric propulsion, and its baseline mission is to fly by a long-period comet. But the design allows it to target an ISO if one is discovered with the proper geometry and velocity. Having such a dedicated standby mission greatly increases our ability to intercept the next interstellar visitor. Building mission flexibility is another strategic axis. Spacecraft with modular payloads, large delta-V margins, the ability to launch quickly, and trajectories that exploit gravity assists can stretch our reach. Mission studies show that using a solar obverse maneuver can make some ISO intercepts feasible that otherwise would not be. Incorporating such options into standby spacecraft design increases the intercept envelope. For example, research modeling minimum energy transfers to 3I/Atlas shows that a carefully planned trajectory launched in months following detection might require a delta V within current capabilities. Survey systems designed for rapid identification, orbit refinement, and prioritization of potential ISO candidates will improve intercept odds. For example, synthetic population modeling suggests detectable ISOs cluster near the ecliptic and solar apex, indicating that surveys focusing on these sky regions will improve success rates. In practice, this means integrating dedicated pipelines within large survey telescope operations to flag hyperbolic objects and feed alerts to mission control. In addition to hardware, strategy demands operational protocols, establishing a decision tree for ISO interception, when to declare an object as candidate, how to assess delta V feasibility, when to launch, when to fall back to remote study. Having policies and cross-agency cooperation pre-agreed will speed decision-making. Ensuring launch vehicles, communication networks, and mission teams can mobilize quickly is vital. Another future strategy is reusable or multi-target spacecraft. A spacecraft designed to visit an ISO could have secondary objectives if the intercept fails, such as a long-period comet or Centaur object, ensuring mission value is not lost. This flexibility reduces risk and cost overhead. White paper studies suggest missions to ISOs should be multi-purpose to justify cost and design complexity. Looking ahead, one can imagine a network of small interceptors, CubeSat or SmallSat class, deployed in heliocentric parking orbits at 1 AU with propulsion and onboard instrumentation capable of serendipitous ISO encounters. With the detection rate of ISOs increasing, having multiple cheap standby spacecraft increases probability of intercept. Finally, an important strategic consideration is budgeting and supporting infrastructure. Missions for ISO interception will compete with many other space science goals. Building cost-effectiveness, demonstrating viability on smaller missions, and establishing the science return for sample analysis, exoplanetary system comparison, astrobiology, will help secure funding. Recognition that ISOs bring unique insights into planetary formation and galactic chemistry can justify the investment in rapid response capability. In the years ahead, as the detection of interstellar objects becomes more routine, the goal might just shift from observe if we can to intercept when we can. Public engagement and media coverage of 3I/Atlas. The arrival of 3I/Atlas has ignited a wave of public fascination, media headlines, and intense scientific communication efforts. From the earliest discovery announcements to debates over alien probe hypotheses, the way this interstellar visitor is being presented to the wider world provides a revealing case study in how science intersects with storytelling, expectation, and responsibility. When the object was first detected, media outlets quickly picked up the news of the third known interstellar object entering our solar system. The simple headline, "Visitor from Beyond," was compelling enough that many lay readers assumed extrasolar origins automatically meant exotic or extraordinary. Yet from the start, communications specialists emphasized that 3I/Atlas posed no impact threat to Earth. Soon after the announcement, the coverage shifted into more sensational terrain. An article in the New York Post suggested that 3I/Atlas was emitting metal alloy never seen in nature, and quoted a prominent scientist suggesting it could be an alien craft. That kind of framing made for gripping headlines, but also raised concerns among scientists about public misinterpretation. Avi Loeb wrote a piece titled "The Media Tsunami of 3I/Atlas," describing how phone calls from Congress and Reuters arrived simultaneously and how managing press interest became a task in itself. Behind the media storm, scientists and outreach teams faced the challenge of balancing accessibility and accuracy. On one hand, the discovery is inherently dramatic, a rare interstellar object, older than our solar system, speeding through space. On the other hand, many caveats apply. We lack full details. Many interpretations are preliminary, and extraordinary claims still require extraordinary evidence. Public engagement has also taken the form of real-time streaming of observation events. Media articles described how science communicators watched astronomers view 3I/Atlas in real time, illustrating the excitement of toggling telescopes, adjusting exposures, and catching the faint object as it emerged from the sun's glare. These behind-the-scenes glimpses offer the public a window into how scientific research unfolds, not as polished slides, but as a dynamic process. The alien probe angle persists in popular coverage because it taps into deep cultural themes. Are we alone? Has another civilization sent something our way? While many scientists caution against jumping to that interpretation, the possibility captivates the public imagination. NASA's official response to such claims emphasized that no artificial signature has been confirmed, but that the object remains under study. This responsible statement helps align expectations. The idea of alien technology is enthralling, but remains speculative. Audience interest also extends to visual spectacle. Observers reported a strange green glow from the object during a lunar eclipse, prompting articles under titles like "Strange Green Glow from Interstellar Comet 3I/Atlas has scientists puzzled." Such imagery, an object glowing green against the dark sky, dramatizes the science. At the same time, it invites misinterpretation. Green glows are often natural due to CN or C2 molecules, but when tied to an interstellar visitor, the public may assume something alien is at work. Another facet is how outreach portals place the object in broader context. For example, an article on space.com explained how objects like 3I/Atlas may be far more common than previously thought, saying there is almost always one within the solar system, though most go unnoticed. This helps temper expectations. The discovery is rare in human terms, but may be ordinary in galactic terms. That sort of framing helps the public grasp both the uniqueness and the routine potential of such visitors. Institutional communication has also had to respond quickly. The NASA science page clearly states the closest Earth approach and that the object is being studied as a scientific opportunity. That calm, factual voice contrasts sometimes with sensational headlines and helps maintain scientific credibility in the public realm. The dynamic between curiosity and caution is always present. On one hand, scientists recognize the chance to engage the public in planetary science, astrobiology, and space missions. On the other hand, they recognize the risk of miscommunication. Making premature claims about alien probes may undermine public trust if later retracted. Some outreach professionals emphasize transparent explanation of uncertainties, erring on the side of, "Here's what we know so far, here's what we don't." Science journalists play a key role in that process. Coverage often includes quotes from mission scientists, visualizations of the object's trajectory, commentary on what this means for our understanding of the galaxy. But some stories lean toward alien headlines, which means the scientific community must actively engage with the media and public to correct myths or clarify misinterpretations. The new Northeastern University article noted that despite early speculation, the object was likely rich in carbon dioxide and exhibited behavior consistent with other comets, though unusual. That kind of sober discourse helps balance dramatic framing. Public curiosity also works its way into educational outreach. Planetariums, observatories, citizen science groups held live viewing events, online forums, and commentary sessions aimed at ordinary skywatchers. Many asked how to spot the object, whether it would be visible to amateur telescopes, and what it might mean for life beyond Earth. With instant global access to images, telescopes, and commentary, any unusual feature or claim, such as metal alloy never seen in nature, can spread quickly. Scientists must anticipate not just questions, but misquestions. What if the public expects alien probes before the data are in? What if early sensational claims lead to disillusionment later? Responsible communication builds trust by emphasizing uncertainty, providing context, and inviting interest, without overpromising. For many people, the idea that Earth is part of a vast galaxy of star systems, and that objects can literally drift between them, profoundly alters perspective. The storytelling around 3I/Atlas includes both the hard science, spectra, trajectory, composition, and the larger themes, connectedness across the stars, the possibility of galactic debris exchange, maybe even life's ingredients wandering between systems. This human interest layer helps expand the reach beyond scientific journals into classrooms, public talks, and broader cultural reflection. Yet the human impact also means scientists must manage expectations. If early reports promise alien contact and no such sign materializes, public optimism could vanish. One outreach expert pointed out that witnessing such a discovery is a source of wonder, but that wonder must be grounded. Researchers now work not just for fellow scientists, but for a global public, and their communication strategies reflect that. Open data releases, press briefings, live commentary, and accessible summaries all reinforce transparency. The NASA multimedia page for 3I/Atlas includes images, video updates, and public-friendly statements. That accessibility helps demystify science and invite public participation. How we talk about such objects, what we highlight, what we refrain from, how we balance excitement and accuracy, shapes not just public understanding of this visitor, but public trust in science itself. Theoretical models of ejection and travel of interstellar objects. Studies have shown that when a system hosts large gas giants, especially ones that migrate or scatter each other, the resultant gravitational turmoil can fling planetesimals, icy or rocky bodies, onto escape trajectories. In a key study, scientists argued that planet-planet scattering is the leading mechanism by which planetesimals gain enough energy to escape into interstellar space. They pointed out that unstable systems, where giant planets undergo chaotic rearrangements, can eject large numbers of smaller bodies. That same study acknowledged that the process is self-limiting. A planetary system cannot eject matter indefinitely because its population of unstable planetesimals is depleted over time. Other theoretical work explores how stellar flybys, close passages of other stars early in a star's life, also perturb outer planetesimal belts and increase the likelihood of ejection. A 2021 study by Falzner and colleagues found that close stellar flybys can be a significant channel for generating interstellar objects, especially in dense stellar clusters. In such encounters, the gravity of a passing star can nudge planetesimals onto very high-velocity paths, boosting the number of ejections. These mechanisms work in tandem. Planet-planet scattering stirs things up inside the system. Stellar flybys give added push from outside. When a planetesimal receives one of these kicks, whether from a planet or star, it may end up on a trajectory that allows escape from the host star's gravitational well. The ejection velocity, the excess speed beyond escape, is a key factor. Some recent simulation work suggests that typical ejection velocities are of the order of a few kms relative to the host star's escape speed. For example, A team ran more than 2,000 N-body simulations and found ejection velocities clustering around 1–2 km per s for many systems, under certain architectural conditions. These velocities, modest though they may seem, become significant when combined with the host star's own motion through the galaxy. Once free, the object becomes an interstellar wanderer. From the moment of ejection onward, the object enters a long interstellar journey. It travels through the galactic environment, subject to gravitational tides from the Milky Way, perturbations from passing stars, encounters with giant molecular clouds, and the general gravitational potential of the galaxy. Over millions or billions of years, the object's trajectory is altered, its original velocity vector smeared, and its path toward another star system randomized. Work by Marcetta and Coas in 2023 used synthetic populations of ISOs within the solar neighborhood to show that the population is shaped by both the ejection mechanisms and the galactic dynamics that follow. The timescale of travel can be vast. For example, in studies of Oumuamua, authors estimated that it might have circulated through the galaxy many times before arriving here. During interstellar travel, the object remains largely untouched by strong heat or radiation from a nearby star, unless it passes close to one. That allows its internal structure, volatile inventory, and surface features to age quietly. Then, when it enters a new star's domain, solar heating, radiation pressure, and collisional interactions may suddenly activate the object, triggering outgassing, cometary activity, or fragmentation. Simulations indicate that systems with giant planets and significant planetesimal disks can eject large numbers of objects. According to one paper, only a small fraction, about 0.1 to 1%, of planetesimals may undergo tidal disruption during ejection, passing so closely to a giant planet that they break apart and get thrown out. This may explain why some interstellar objects have small sizes or unusual shapes. Ejection processes might fragment bodies, strip volatile layers, or alter rotation states. Ejection mechanisms thus produce a spectrum of interstellar bodies, some icy and comet-like, some rocky or devolatilized, some small, others large. The theoretical models further suggest that the mass of ejected planetesimals per star could be large. One estimate proposed that about 1 Earth mass of planetesimals might be ejected per solar mass of stars. But this assumes a size distribution and ejection efficiency that remains uncertain. What about an object like 3I/Atlas? Its high excess velocity and hyperbolic trajectory imply that it received a substantial kick at ejection. That may indicate a system with a particularly strong scattering event, perhaps multiple giant planets, a binary star companion, or a close stellar flyby. Its composition hints at a distant cold formation region and a violent ejection path. The theory of ejection then links to formation environment. Outer planetesimal belts, high eccentricity giant planets, or cluster environments rich in stellar encounters may all contribute. Some of the theoretical literature suggests that over billions of years, interstellar objects could lose much of their volatile content, making them less comet-like when they arrive. That may explain objects like Oumuamua, which showed little to no outgassing, but Atlas shows strong volatile activity, suggesting it may be younger, has spent less time in space, or retains deep volatile reservoirs. That in turn constrains ejection times, travel distance, or protective shielding of volatiles. The interplay between ejection age and preserved volatile content is a growing theoretical theme. The galactic dynamics of ISOs also raise the possibility of capture by future star systems, though the probability is low. A detailed modeling study in 2024 looked at the phase space of possible captures, indicating that weak capture of an ISO into a new solar system orbit is possible if the object passes through a region of the Hill sphere under favorable conditions. Thus, not all ISOs simply pass by. They might linger, perturb outer belts, or even become temporary or permanent members of systems other than their origin. As the models grow more sophisticated, researchers are using ISO observations to infer constraints on planetary system architectures across the galaxy. For instance, one group argued that the distribution of ejection velocities can be a memory of the parent system's architecture. Slow ejections may come from stable planetary systems, while higher velocities imply more violent early histories. Thus, observing objects like 3I/Atlas not only provides data on one body, but also clues to exoplanet system evolution. The travel path of an ISO is shaped by the galactic potential, the combined gravitational influence of the Milky Way's stars, gas, dark matter, and distribution of mass. As an object moves, its orbit through the galaxy is slowly perturbed, shifting its trajectory and velocity over time. The longer it travels, the more its origin direction is blurred. That is why tracing back an object to a specific star system is extremely challenging, even with precise astrometry and stellar catalogues. Population synthesis simulations, such as those by Marquetta, estimate the expected flux of ISOs in our solar neighborhood and consider how survey selection biases shape what we observe. These models show that if planet scattering and ejection are common, then thousands of ISOs may traverse the solar system over the age of the Sun, though only a few large ones may be bright enough to detect. That supports the notion that while 3I/Atlas appears rare, similar objects may be much more common than our samples indicate. In addition to ejection from planetary systems, other mechanisms theorized include late-stage stellar mass loss or binary star interactions. For example, when a star evolves off the main sequence, mass loss can reduce its gravitational hold on orbiting bodies, allowing planetesimals to drift away. Some studies of interstellar comets suggest that post-main sequence star systems may contribute. Meanwhile, binary systems with dense stellar companions can accelerate ejection to higher velocities. Some models for Oumuamua invoked binary star tidal disruption as a possible origin. These mechanisms highlight the diversity of pathways by which interstellar objects may originate. Understanding these theoretical models helps explain why we observe objects with certain velocities, compositions, and incoming directions. It provides a framework for interpreting anomalies. If an object shows an unusual chemical signature or a particularly high velocity, we can ask whether it was ejected via a strong stellar encounter rather than gentle planet scattering. The models of ejection and travel, then, are scaffolding for interpreting each ISO we detect. The ejection and travel of interstellar objects are governed by a sequence of dynamic processes. Each step leaves an imprint on the object, its speed, composition, age, trajectory, and by studying these bodies, we begin to unlock those imprints. The theoretical models remain subject to refinements and uncertainties, but they provide the basis for understanding how a tiny fragment cast off a distant star system can eventually cross the vast gulf of space to visit our solar neighborhood. Future observational campaigns and what to expect next. As the 3I/Atlas continues its passage through the solar system, astronomers around the world are mounting an ambitious series of observational campaigns aimed at taking full advantage of this unique opportunity. From ground-based telescopes to space observatories and even planetary orbiters at Mars, the planning for what comes next touches on imaging, spectroscopy, dust and gas monitoring, and tracking how the object evolves as solar heating intensifies. According to NASA, the object would remain visible to ground-based telescopes through September 2025, after which it would pass too close to the Sun for Earth-based observatories to easily observe. Then, the object is expected to reappear on the far side of the Sun by early December 2025, offering a second window for observations as it recedes. In that first phase, observatories such as the Hubble Space Telescope and large ground-based facilities like the Gemini North Telescope have already been engaged. Meanwhile, space missions are also stepping in. Notably, the Parker Solar Probe is slated to observe 3I/Atlas, using its WHISPER instrument between late September and early November 2025, as the object passes close to the Sun and becomes visible from a vantage closer to the solar environment. Observing from such a vantage offers advantages: less interference from Earth's atmosphere and a different geometry for examining dust and gas, illuminated by intense solar radiation. Another major upcoming campaign takes advantage of spacecraft orbiting Mars. Orbiters such as the Mars Express and the ExoMars Trace Gas Orbiter plan to attempt imaging and spectroscopy of the object from a closer vantage than Earth can provide. They hope to use high-resolution cameras like HRSC and CASSIS, plus spectrometers like NOMAD and OMEGA to probe the dust structure, coma composition, and potentially assess nucleus shape. The possibility of getting Mars-based or orbit-based imagery offers a complement to Earth-based observations and opens a novel observing geometry. As 3I/Atlas approaches perihelion around the 29th of October, the changing solar heating will trigger increasing activity. Monitoring that evolution is high priority. Infrared spectroscopy from JWST and other IR instruments can track molecular emissions as the object warms. Observing that transition offers insight into what happens when an interstellar object meets strong solar heating for the first time. Reappearance in early December opens the possibility of monitoring how the coma dissipates, how dust production rates decline, and whether non-gravitational forces alter the trajectory measurably. These data refine how interstellar objects lose mass, how they behave outside familiar solar system conditions, and offer constraints on nucleus durability and volatile inventory. ESA notes that the JUICE mission is scheduled to attempt observations in November 2025 using cameras, spectrometers, and particle sensors. That adds yet another platform and vantage point for the outbound leg. Integration of citizen science telescopes, Unistellar and others, is already contributing dozens of observations of 3I/Atlas's light curve and brightening behavior. Encouraging amateur astronomers to monitor the object expands the dataset and prolongs monitoring as professional telescopes shift focus. Another promising extension is polarimetric and dust grain studies. Instruments on ground telescopes like VLT's Force 2, Alphosk Knot, and others are being scheduled to measure polarization phase curves of the dust, which can hint at grain size, composition, porosity, and structure. Early results suggest an unusually deep negative polarization branch, 2.7% at 7 degrees phase angle, for this object, reflecting dust properties unlike typical solar system comets. Additional observations as geometry changes will refine interpretations and may highlight dust mechanisms unique to interstellar bodies. To maximize science, coordination among observatories is key. Space-based missions and Mars orbiters must step in during Earth's downtime. Standardized pipelines for archiving and sharing results, photometry, spectra, images, will ensure the object's behavior is tracked continuously. The object's rapid motion and changing brightness demand that exposure times, pointing strategies and filters be adapted quickly. Data reduction must keep pace so follow-up observations can adjust. Scientists anticipate that the observational campaigns may answer several open questions: more precise nucleus size and albedo, detailed volatile inventory, dust production rate as a function of solar distance, confirmation or refutation of unusual metal or dust emissions, monitoring for fragmentation or disintegration, measurement of non-gravitational accelerations, and refinement of the object's ejection history from its parent system. If 3I/Atlas breaks up, new fragments could appear and offer even more material to study. If it survives and remains active, it may show seasonal variation in activity as it moves away from the Sun, data that no previous interstellar visitor has offered. What if it is technological? Imagining the possibility that 3I/Atlas might not simply be a crazy exotic comet, but something intentionally manufactured brings profound implications, both scientifically and culturally. If the object turned out to be technological in origin, an artifact of an extraterrestrial intelligence, it would fundamentally shift how humanity perceives itself, its place in the cosmos, and its responsibilities toward the broader universe. Exploring this scenario is speculative, but doing so helps frame why the investigation matters beyond raw data and why the stakes feel so large. If 3I/Atlas were confirmed to be artificial, the very premise that humanity is alone or unique in the galaxy would be challenged. The widely held assumption that interstellar objects are inert, natural bodies ejected from distant star systems would need to be expanded to include intelligent origin. As one prominent thinker argues, the detection of an alien probe would mark the most consequential discovery in human history. The idea would ripple through science, philosophy, religion, politics, and public consciousness. The realization that others have developed spacefaring technology changes the narrative of our cosmic isolation. Culturally, the confirmation of technological origin would raise questions of scale and maturity. How old is the craft? What civilization built it? What was its purpose? Was it intended as exploration, observation, communication, or something less benign? The literature on Bracewell probes, self-replicating or autonomous interstellar scouts placed intentionally by advanced civilizations, would suddenly move from speculation to context. Humanity would find itself in the presence, however indirect, of a technological expression of another species, and would have to reckon with its own technological infancy in comparison. In practical terms, discovering 3I/Atlas is technological would create new responsibilities. First, there is the stewardship of what might be a priceless artifact. Protocols for handling, observing, and perhaps even interacting with such an object would need to be developed. Who makes decisions? Which nations or international bodies govern the response? If an object like 3I/Atlas shows attributes of maneuvering or design, then our frameworks for cosmic artifacts must change. Second, there is the question of communication. Should we attempt to send a message? Should we take a passive stance and just observe? Some argue that just knowing we are not alone could change how we think about our future. The potential for dialogue or the recognition of persistent silence carries enormous weight. If the craft is technological and possibly directed at or surveilling our system, then the implications for planetary defense change dramatically. The blog post by Loeb, "What Should Humanity Do on the Day After an Interstellar Object is Recognized as Technological?" outlines how our response mechanisms would need to shift from asteroid deflection to interaction with potential alien artifacts. There would be unsettling questions. Was the object sent as a benign observation vehicle or as something more ominous? Could it carry subprobes, as some press coverage speculated about 3I/Atlas releasing mini-probes that might appear as UAP? The path of response would include not simply science, but diplomacy, ethics, and perhaps even interplanetary law. Humans have long assumed they were alone, or at least one among many but separated. Confirming technology from elsewhere would collapse that boundary. It may spur humanity to see itself less as isolated earthbound species and more as part of a galactic community, or perhaps a watched one. The humility required by that shift could foster cooperation on Earth, new investment in space science, or conversely, fear and competition. If the object was sent for observation, do we respond? Do we broadcast our presence or remain silent? If we are being observed, what does that mean for our behavior? Some futurists argue that recognizing we are not alone imposes a responsibility to behave as custodians of Earth, not just as isolated beings. The vulnerable world hypothesis, for example, suggests advanced civilizations might self-destruct when they acquire certain capacities. Perhaps our recognition of others serves as a mirror. Discovering an alien artifact could lead to deep introspection about our technological trajectory, our readiness for contact, and how we manage cosmic risks. On the scientific front, a technological 3I/Atlas would open a new branch of research. Alien engineering, long-duration durability of spacecraft, interstellar travel strategies by other civilizations, and the origin conditions of that civilization. We would try to reverse engineer design, materials, power systems, intentions. The modeling of natural versus artificial signatures would shift to active forensic investigation. What metals are present? What isotopes? What wear patterns? What internal structures? We might ask, did the object come complete, or is it a fragment? Was it sent intentionally toward us, or is it drifting? Are there purposeful emissions or communications to detect? Just the possibility alone invites humanity to create protocols for recognizing non-natural phenomena. It invites design of space missions to intercept or rendezvous with such objects. It pushes the case for readiness, to survey, detect, and respond to objects not just from our solar system, but from interstellar space. The mere fact that scientists like Loeb and colleagues publish models that treat 3I/Atlas as possibly hostile or engineered is a signal that our scientific horizon has expanded. Considering that scenario also reminds us of our limitations. If another civilization is sufficiently advanced to dispatch interstellar probes, we may be in a very different league. Our ability to intercept or influence such objects might be negligible. The question then is, do we adopt a posture of humility and observation, or do we strive to catch up? How we respond says much about humanity's aspirations. If it is natural, it still connects us to other star systems and opens the possibility of material exchange across the galaxy. If it is technological, the implications are even larger, a door open to interstellar civilization. Either way, the notion that an object arrived from beyond, carrying information, and possibly intent, from another world, forces humanity to reconsider its role, its responsibilities, and its readiness to engage with the wider cosmos. Why study these visitors? Studying rare wanderers like 3I/Atlas goes far beyond the immediate thrill of discovery. It reaches into the fundamental questions of how we explore, learn, and connect with the cosmos. One of the prime reasons to study interstellar objects is curiosity in its purest form. Objects like 3I/Atlas are physically and mentally stimulating because they come from somewhere else. When we study them, we aren't just looking at objects. We're looking at interstellar material that links us to a much larger context of cosmic heritage. From a planetary science perspective, studying such visitors challenges and extends our understanding of how planets form and how planetary systems evolve. Most of our models for planet formation, disk chemistry, migration of planets, ejection of small bodies rely on data from our solar system. But an object like 3I/Atlas gives us a sample of a different system. By comparing it, we gain new insights into not only what our solar system is like, but what it might not be like, thereby helping frame where it lies in the spectrum of planetary systems in our galaxy. If small bodies can be ejected from one star system and travel through interstellar space to another, the possibility arises that organic molecules, volatiles, or other building blocks of life could likewise traverse interstellar terrain. While this remains speculative, studying a visitor like 3I/Atlas helps test how stable ices and organics persist in interstellar conditions, how long they survive, and how they respond to solar heating when they finally approach a star. Articles suggest that each ISO is a probe into the chemistry and dynamics of the galaxy's small body population. In other words, these interstellar travelers might tell us something about how widespread life-friendly chemistry is, or at least how materials move among star systems. When you study objects that come from outside the familiar context of our solar system, you must allow for surprises. 3I/Atlas already shows behavior that challenges typical cometary models. These anomalies force scientists to revisit assumptions, refine models, and expand the horizon of what is considered normal. That is a healthy feature of the scientific process. When observations surprise you, it means your understanding needs deepening. This readiness to be surprised is part of why studying them matters. They are wildcards, rare but potentially transformative. In practical terms, studying interstellar objects builds scientific capacity and innovation. The techniques required, rapid detection, multi-wavelength follow-up, coordination among ground and space observatories, and even mission planning for interception are more advanced than routine surveys of solar system objects. For 3I/Atlas, we are mobilizing telescopes, missions, instruments, and protocols under time pressure. That process strengthens the infrastructure of planetary science and space exploration. It trains observatories and scientists to respond quickly, coordinate globally, and integrate large datasets in real time. In a sense, by preparing for interstellar visitors, we improve our ability to handle unexpected events in space. from comets to mini-asteroids to potentially hazardous objects. The white paper on advancing interstellar science argues for a global framework to ensure coordinated responses to such objects. The upsides include better systems, data infrastructure, international cooperation, all of which have broader benefits. There is also a broader human dimension. When the public hears about 3I/Atlas, they often see visitor from another star, and that story resonates. The connection helps science be more than sterile data. It becomes part of the human story. The future may hold more discoveries, perhaps more frequent interstellar objects as telescope capabilities advance. This means scientists and mission planners are gearing up for a future where interstellar visitors are common enough to plan for, monitor, and perhaps intercept. That infrastructure will benefit planetary defense, survey science, space mission engineering, and our readiness for unexpected cosmic events. In that sense, studying objects like 3I/Atlas is forward-looking. It's investing in a science and engineering foundation for a more connected galactic era. The study of 3I/Atlas and other visitors also underscores the value of cross-disciplinary science. Astronomy, planetary science, chemistry, dynamics, and even astrobiology come together. Discovering and characterizing an interstellar object demands teams of observers, mission designers, data analysts, modelers, and communicators. The process builds scientific networks and sets up shared knowledge bases. That breadth of collaboration supports the scientific ecosystem and lays groundwork for future discoveries. By engaging with the alien materials, unfamiliar chemistry, and distant origins of 3I/Atlas, we affirm something central to science and human nature: a willingness to reach outward, to ask questions no one has asked before, and to embrace the unexpected. Has our solar system sent out material to other stars? Just as alien debris has crossed our threshold, pieces of our own solar system may have long since slipped free of the sun's grasp, drifting between the stars. Somewhere out there, in the vast dark ocean between suns, a small rock or fragment ejected from the early Earth, Mars, or Jupiter's moons may be silently passing through a foreign planetary system, perhaps even glinting faintly in the light of another star, just as 3I/Atlas glinted in ours. The physics that allow material from elsewhere to reach us are symmetric. Every time a comet from the outer reaches of our solar system is perturbed by Jupiter's gravity, there is a chance that it is not merely flung into a more eccentric orbit, but ejected entirely. Over billions of years, the solar system has been a restless place, shaped by collisions, migrations, and gravitational encounters. The early epochs in particular were chaotic. Planetesimals collided violently, planets moved inward and outward, and countless fragments were launched into interstellar space. It is estimated that during the solar system's youth, a vast amount of debris, possibly equivalent in total mass to several Earths, was expelled by the gravitational slingshots of the giant planets. Each one of those objects, tumbling into the dark, became an ambassador of our system, carrying within it the chemical fingerprints of the sun and the elements that built our world. Even now, the process continues. Jupiter and Saturn, acting as cosmic catapults, still occasionally send small bodies into escape trajectories. A comet that passes too close to these giants can receive just the right kind of push to reach a velocity greater than the sun's escape speed. When that happens, the object is effectively lost to us forever. It becomes interstellar, no longer bound to our star, but to the galaxy. From that moment onward, it drifts on a path that may take millions of years before it ever encounters another system. Some of those ejected fragments might eventually wander close enough to another star's gravity to be drawn inward. There they could appear to that civilization's astronomers, just as 3I/Atlas appeared to ours. If that exchange is real, then our solar system has been part of a long and silent conversation between stars for eons. The matter that makes up our worlds, the ices, the silicates, the metals, does not belong solely to us. It moves between systems, carrying with it records of temperature, radiation, and chemical evolution. In that sense, interstellar space is filled with the dust and relics of countless stellar histories, blended over time into the diffuse medium that seeds new generations of stars. Every interstellar comet may therefore contain material once touched by other suns, just as some of the comets in our system may carry within them atoms that once orbited distant stars. On these scales, the boundaries between star systems blur, and the Milky Way itself begins to look like one continuous ecological system, with matter flowing and recycling across tens of thousands of light years. Powerful impacts on early Earth or Mars could have thrown fragments containing microbial life into space. If any of those fragments achieved escape velocity and were ejected by planetary encounters, they might still be drifting now, carrying dormant life through the cold vacuum. Over immense spans of time, one of those fragments might cross paths with another habitable world, falling through its atmosphere and delivering traces of organic material. The odds of that are astronomically small, yet given the vastness of time and number of ejected fragments, it is not impossible. It would mean that the story of life, like the story of matter, is one of migration and exchange, not confinement. In this view, the solar system has already been broadcasting its legacy for billions of years, not through radio signals or probes, but through simple physical processes. Every asteroid shattered by impact, every comet perturbed into escape, becomes part of an outward flow of matter that may outlast the Sun itself. A fragment of Earth's crust, perhaps blasted free during the late heavy bombardment, could now be a billion years into a voyage between stars. Another, from a long-lost icy moon, might one day be captured by a distant system and fall into orbit around an alien world. These are journeys beyond any we could engineer, slow and unending, carried forward by gravity alone. They are the natural version of what we dream of achieving with technology: interstellar travel, albeit unintentional and wordless. When scientists model how much material leaves a planetary system over time, the results are staggering. During the solar system's early evolution, as Jupiter and Saturn migrated to their current positions, their gravitational interactions would have ejected countless trillions of small bodies from the primordial disk. Each of these icy fragments would have carried isotopic ratios and mineral compositions unique to our system's chemistry. Over billions of years, that material has been slowly dispersing into the galaxy. Some researchers estimate that there may now be billions of interstellar comets roaming between stars for every star in the Milky Way, a galactic population of wanderers, each bearing the imprint of its origin. If that is true, then it follows that many of those fragments come from our own Sun. Somewhere out there, lost in the immensity of space, our system's fingerprints are already scattered across interstellar distances. There is something quietly moving about this realization. During Earth's violent early history, impacts from asteroids and comets regularly ejected fragments into space. Some of these fragments achieved escape velocity, breaking free of Earth's gravitational hold. Over millions of years, gravitational interactions with the Moon and other planets could have nudged a small fraction of them onto paths that would lead them out of the solar system entirely. If any of those fragments bore traces of Earth's surface, minerals, fossils, or organic molecules, they would now be silent witnesses to our planet's existence, drifting endlessly through the galaxy. In a way, they are the truest form of time capsules, records of our world before there were humans, carrying memories that no civilization can recall, but that nature preserved and sent outward into the dark. Even human activity, brief as it is compared to the solar system's age, has already begun contributing to this outward flow. The spacecraft we have launched, Voyager 1 and 2, Pioneer 10 and 11, and New Horizons, are now on interstellar trajectories. These machines, though small and fragile, will outlast the Earth itself. In millions of years, they will pass between the stars, carrying plaques and discs etched with symbols of their makers. They are the artificial complement to the natural fragments that have been leaving our system since its birth. Long after the Sun expands and engulfs the inner planets, these spacecraft will continue their journey. It is possible that one day they will drift into another star's domain, where an alien astronomer might detect their metallic glint and wonder about their origin, just as we now wonder about 3I/Atlas. Each interstellar object we observe is a reminder that our own system has been performing the same act since its earliest days. And if someday another civilization observes a strange, fast-moving object passing through their sky, analyzing its unusual orbit and metallic traces, they might be looking at one of our own, an echo of the sun's creation, a relic of a civilization long gone, still voyaging through the deep between stars. What do you think of the likelihood of 3I/Atlas being alien in origin? And what other topics would you like videos on? Send us your thoughts in the comments, and if you enjoyed what you saw, please leave a like and subscribe.